Hello. Oh, hey, I need to go to the chair, right? All right. So welcome to the afternoon session on our last day. I'm super excited that Justin Solomon is here. He's an associate professor in the Department of Electrical Engineering and Computer Science at MIT. He's the principal investigator of the Geometric Data Processing Group and works on problems in shape analysis, machine learning, graphics from a geometric perspective. And you may know him from his book on numerical algorithms, or perhaps his highly or extremely highly cited SIGGRAPH papers, or likewise as the person to ask all your important questions about optimal transport, or likewise as the organizer of the Summer Geometry Initiative, which introduces a diverse and international group of undergraduates and grad students to the field of geometry processing. I'm trying to promote all these things that everyone needs to know about. So that said, professor, winner of many awards, and accomplished cellist, and overall super nice guy, Justin, the floor is yours.
All right, well, thank you, Paul, for that extremely generous introduction. I'm now suitably terrified of the talk and of dropping this microphone. Right, well, it's a pleasure to be here and to speak with you all today and to share a little bit of research from, mostly my students. Of course, the faculty don't get to do any of the exciting and fun stuff. We're just here to promote them. But since we have a little bit of limited time, I thought I would tell you some about the research that our group is doing, specifically kind of at the intersection of machine learning and computer graphics, which conveniently fits together with many of the other talks that we've heard, including from Manolis yesterday, and in a funny way, the keynote this morning on music processing. So without further ado, I guess we already had a pretty comprehensive introduction here. Oops. Everything's kind of loud. Hello? Is that better? Cool. It's very difficult to judge from here. Right, so I'm coming to you all from Boston, which is not all that far away, so I really strongly encourage all the students and faculty in Montreal to swing by. And I lead a group at MIT that is titled the Geometric Data Processing Group. Now, at MIT, they require us to give each of our research groups different kind of taglines. And the reason that we settled on this particular phrase was that it allowed me to have an extremely vague research agenda. So in particular, our group is sort of split half and half among some students that are working on computer graphics, computer vision style research problems that kind of look at typical approaches to processing geometric data. Right? As we know, geometry in computer graphics comes in many forms. It comes in meshes and implicit surfaces, and it comes from simulation and 3D scans. And this provides us no shortage of interesting data to work with in the kind of somewhere in between the machine learning and even just classical geometry processing world. On the other hand, kind of an interesting thread that happened in my own research and now has spread to my graduate students and postdocs is that many of the techniques and intuition that we've built up for low-dimensional geometry processing that we see in the computer graphics world helps us get a little bit of a toehold into how to think about more abstract data processing problems. So for instance, Paul mentioned optimal transport, which was the area of my PhD thesis. Interestingly, this was an area of research that originally was very popular in computer graphics and vision for like morphing images into each other and so on. But these days is really used for inference problems and high-dimensional kind of statistics, like what you see in generative adversarial network. And so this kind of funny thing happened in our research group, which is that it has broadened very much. And so it's been a lot of fun for me because every person that I speak with gets to look at a completely different topic and a different area of mathematics. In any event, in 30 minutes today, I can hardly summarize all those different directions, so I thought I would pull out just one kind of thread from our research that has been one of the more popular things that we've worked on in the last couple of years, and that's machine learning from geometric data. So the basic idea here is that we want to load in a shape and then use machine learning tools to infer some information about it, right? So the most basic instances of this problem might be that you load in, for example, a LiDAR scan, like what you see on the left-hand side here, or a triangle mesh, like the bunny on the right. And the goal might be to do something simple, like label, is this a bunny or some other object? But these days, of course, those basic operations get incorporated into larger systems for things like object detection, finding vehicles and pedestrians and so on in a 3D environment. And so these kind of basic building blocks that we're working on really get plugged into a lot of these larger applications. Now, when we started working on these problems many years ago, there really were many different challenges in learning specifically from geometry as opposed to learning from some of the modalities that are maybe more popular in the early computer machine learning literature. And I think what we saw in the really early literature on how to learn from a shape looked something like this. So we have, a sort of, and of course this is a vast oversimplification, and Manolis will give me a hard time, during the break. But essentially, there's this big set of popular tools for machine learning out there, whether it's, PyTorch or TensorFlow, what have you. And these are extremely successful for many different instances of machine learning, right? Specifically, I think we saw, processing just abstract data points, natural language processing, and image processing. And so there's a totally reasonable inclination to use those tools as a starting point and to say, how can I take the success that's worked really well in these other domains and transfer it to geometry? But in essence, what that makes you do is kind of engineering with a certain set of constraints, right? Like essentially, you're developing geometry tools that are working with the kinds of operations that were already built into PyTorch and TensorFlow. And unfortunately, those tools are just not always the right thing for the job. In particular, when it comes to visual computing, I think the typical machine learning architecture that we're all familiar with is the convolutional neural network. And the key word here is convolution, right? So a convolutional neural network is used to process, whether it's photographs, or I tried to take the closest projection of the Stanford bunny onto an image grid here. But the reality is that this isn't a great way to communicate a shape. Now, of course, there are many ways to bridge that gap. For instance, maybe you take a volume and you look at the indicator of what's inside of the bunny and what's not. But the reality is that convolution, for example, is just not an operation that we see all that often in geometry processing, at least without a lot of kind of work to kind of bridge the gap between this nice flat image grid and like a curved object sitting in 3D space. And so the question that we set out to answer was like, what if we took that arrow and we kind of pointed it in the opposite direction? Right? Like we look at what sort of operations and computations might make sense to a person in computer graphics domain when they're working with a triangle mesh or a point cloud or whatever your favorite 3D modality is, and can we start from that as a building block and extend into the machine learning universe rather than the other way around? And in particular, there's some basic operations that I think have made sense in the geometry community for a long time. They just don't look like convolution. For instance, oftentimes maybe in point clouds you see things like nearest neighbor search. There's a sort of mesh operations, graph operations that are very typical in computer graphics. And of course, what underlies a lot of modern geometry processing is sparse linear algebra, which until really the last year or two didn't appear in many of these deep learning frameworks. And so essentially, we wanted to ask whether, if we were unencumbered by the capabilities of current machine learning tools, could we engineer interesting techniques that can have good performance for machine learning tasks on 3D geometry, but still look kind of sensible, is the word that I settled on, to somebody that works in this domain before machine learning became so popular. Right? The idea that somehow, it would pass the sniff test when you look at the type of calculations that we're doing on a triangle mesh or a point cloud, even if there's still some neural network sitting behind the scenes. And I would argue that a lot of the operations that were successful in early machine learning plus geometry really didn't pass the sniff test, right? They kind of looked like, take your geometric data, shoehorn it into an image or a grid or some other modality that machine learning handles better, and then do stuff in that domain. So today I'll tell you about two of many efforts that we've had in this space to process different geometric modality. And again, for today, we're going to focus on the simple task of inputting a piece of geometry and outputting a piece of information about it driven by data. Right? Of course, there are many other super exciting problems at the intersection of geometry and machine learning, like generative modeling, creativity, and so on. These are fantastic things to think about, but for today, we're going to keep it simple, because I'm already running late. Right, so we'll first talk about some of our techniques for learning from point clouds, and then we'll switch to the triangle mesh, which interestingly is a more structured object, but I think is a little less studied in the literature here. And so far, the kind of high-level point that I think we'll take away from our research thus far is that different modalities and different applications sort of demand different learning architectures. So we end up in this kind of interesting scenario where you need to know a little bit about your geometry and where it's coming from in order to come up with the most effective and kind of sensible looking learning technique. Now, before I start, I should be really clear here that, of course, all of the interesting work here is carried out by these fantastic students that I have such an exciting opportunity to work with. I encourage you, if you have a hard question, to direct it to Yue and Dima here. They both actually just graduated in the last 3 weeks, and they're off to bigger and better things. And I thought I'd use this talk as a fun way to promote some of their work. So let's get started by talking about point clouds. Now, point clouds are kind of an interesting modality. They show up both in computer graphics and in computer vision. So for instance, here I show you a LiDAR scan of the environment around a car. This was collected using one of those sensors that spins around on the top of an autonomous vehicle. And the basic task that we're often asked to do when it comes to this type of data is to identify things like where are all the cars in the scene, where are the pedestrians, where are the cyclists, because obviously you kind of hope that your autonomous vehicle is at the very least cognizant of that information, plus a lot more. But there's a lot of challenges here. If we think about it, the input modality in some sense is extremely simplistic. It's just a long list of points. And this list of points is not ordered in any particular way, right? It's just the samples that I gather from the 3D environment around my car, and I'm asked to do inference from that information. But already, you can see that obviously a convolutional neural network is not directly applicable here, right? I mean, there's no grid, there's no kind of regularity, and moreover, the sampling here is extremely kind of all over the place, right? You can see the rings of the LiDAR sensor inside of the point cloud itself, which makes for some interesting challenges. Now, if you look in the literature on point cloud-based deep learning, I think arguably one of the earliest techniques was something that was called PointNet. I'm guessing many of the graduate students in this room have played with this tool before. And PointNet was sort of the first attempt at taking deep learning and applying it to point cloud data in a way that really made sense for this particular modality. I should note there was another technique called deep sets, which came out at about the same time and is like roughly isomorphic. But in any event, PointNet does a very simple thing. So it learns a function on R3, like on the space around your geometry, and it evaluates it at every single point in your point cloud. So like if I input this 3D mug over here, then every single point in the 3D mug gets run through the same function independently of all the other points. So in essence, you're kind of taking your geometry and lifting it to some high-dimensional space. And now you have a k-dimensional mug over here. Oops, I think I said n before, but that's OK. And I need to take all of these k pieces of information and then summarize it into a single decision, like is this a mug or is this some other object? And so what they do is they take some permutation invariant operation that takes in a bunch of different vectors in this space and then summarizes. So the obvious one here would be add them all together. I think in practice, taking the max does a little bit better. And this was the basic PointNet architecture. It's extremely simple, right? Every point gets lifted into some other domain independent of all the other ones, and then they get summarized by this pooling operation. And what's actually kind of remarkable about PointNet is how well it does. I mean, this has no knowledge of curvature, bending, stretching, all the things that we think about in geometry. It's just sort of figuring out what pieces of space a given object kind of occupies in some sense. And because of that, there are certain limitations, right? So in particular, if you want to talk about curvature, local neighborhoods, these things that we usually use to reason about geometry, PointNet is really not able to do it, right? There's an extremely small receptive field, which is sort of the buzzword of machine learning for which points talk to which other points, in the sense that in the first layer, nothing talks to anything else, and in the second layer, I summarize all my features in one shot. It's extremely efficient, but it's a bit tricky to work with. So my student Yue set out to take this PointNet architecture and extend it in a way that looked a bit more nuanced when it comes to understanding geometry. And in particular, there were a few considerations that we wanted to think about. Now, PointNet does satisfy some properties that are maybe different from the typical convolutional neural network. It's order invariant. I can shuffle my list of points and inference doesn't change. These days, that sounds obvious, but actually the early point cloud networks didn't have this property. It can capture global information about your object quite easily, but like capturing local neighborhood or local information is quite difficult in this architecture, or like having even medium scale neighborhoods, right? Like separating the back of your chair from the seat or something like that. And so this led Yue to propose a new architecture for learning from point clouds, built from an object called the edge convolution. This drives me a little bit crazy, but apparently you need to use the word convolution somewhere in your learning paper, or else it doesn't count, even though this is, from my perspective, not really convolution in the mathematical sense. But in any event, this edge conv module is extremely simple. So what it does is every point in your point cloud basically gathers some local neighborhood of other points nearby, and it learns a feature which is relating each point to its neighbor, right? So I get basically a learnable function which takes in 2 points and outputs a feature. And then to get a feature for a point, I take all these edges that I've just constructed, and now I apply that pooling operation, which was done over the whole point cloud in PointNet, just to this local neighborhood to put a feature back on that center point. So if you think about it, essentially what's going on in this architecture is it's still taking a point cloud and then mapping it to another point cloud of the same number of points in this feature space. But the way that it's doing that is by gathering local neighborhoods and trying to infer some interesting information about a point and the relationship to its k-nearest neighbors. So that's where it differs from the older PointNet architecture. Now, this is a really kind of simple idea, and indeed, actually kind of an interesting thing that's happened is that this basic idea has now kind of had a bunch of rebirths in different literatures. You'll notice that this formula is very similar to what's popular these days, which is called attention, and actually there's sort of an equivalence there. But one of the really interesting things that we did, and really came as a surprise, is basically just stack these layers on top of each other the same way that you have many layers of convolution in a convolutional neural network. And the really kind of tricky idea here is that a point's local neighborhood changes in every single layer of this network. So we said that a stack of these edge convolution operations, we're going to call the dynamic graph neural network. We squeezed every buzzword into this architecture possible. But the basic point here is that we have many layers of edge conv stacked on top of one another. And every time that we do that, we recompute a local neighborhood. So again, so here the coloring is like proximity. So like here's a red point, and then it goes from yellow to blue based on distance in your feature space. So on the left-hand side, this is just distance in 3D, right? So it goes from yellow to blue just based on how close you are to the red point. But now EdgeConv starts learning different embeddings of this airplane into more and more abstract spaces. And now we can see that the notion of local neighborhood, in other words, like what points are similar to this red point, starts to change. Right? So originally, it's just like position in 3D. And by the time we get to the end of all the layers of this architecture, you can see that our embedding is clustering the wings together, the engines and the body together in this airplane model. And this was really remarkable to us because we're not adding objective terms that necessarily are that cognizant of these different things. In particular, one thing, I guess this particular example is not great because we're solving shape segmentation, so it actually does know where the wings and the engines are. But even if we solve a task like just distinguish different shape categories from one another, what we found is that these kind of images still look pretty similar. In other words, sort of semantic similarity at a local scale was being learned from the broader machine learning task, which is really remarkable and exciting. So this is work a couple years ago, and since then it became the sort of standard, well, at this point, the standard kind of baseline that everybody kicks on for their own point cloud machine learning problem, but I think that's great and a really great sign that this was somehow a nice fundamental idea. And indeed, we've built on it many different ways to tackle different problems in learning and geometry. So for example, we moved on to studying registration. Many of you are probably familiar with this problem where I have a point cloud that's viewed from 2 different angles, and I want to put them in the same coordinate system. Now, the classical algorithm that you might be familiar with for registration is something called iterative closest point, which has this interesting kind of theorem associated to it, right? Like iterative closest point works so long as you initialize it with the solution of the problem, I think is roughly the theory here. But essentially, what we can do is we can learn features on our geometry that are easier to match than the regional shape itself. Right, so this is kind of an interesting low-level learning task where essentially your training data is just 2 scans of the same object, which is very easy to generate by taking one object and then just putting, randomly rotating or something. And now the training is to try and put them back. right? And so the features that you're learning here are not necessarily semantic, like the previous example, but just like where are useful corners that I can grab onto that make for kind of consistent and reliable registration. So this was a bit of a surprise that these learning tools are not just useful for these sort of high-level learning tasks that we think about, but also low-level things like registration. Sorry, I keep glancing at my watch here because I want to make sure I don't take up too much time from the next speaker. In addition to that, we also have proposed some larger scale architectures for more practical machine learning tasks. For instance, just the last couple of years, we proposed this object DGCNN architecture, which couples with some of these extremely large scale feature computation tools for autonomous driving. There, the point clouds are so large that there's some additional kind of engineering that has to happen. But using an object DGCNN backbone here to do some of the inference in terms of like where the car's pedestrians are. And then actually one of the really interesting observations was that this 3D architecture could even be used for multi-view kind of 2D object detection. So the point here is that I have a bunch of different images of a scene from just 2D cameras attached to a car, and I also know the camera projection for each camera, right, because they're glued onto my car. So I know a little bit about 3D and the relationship between like maybe the positions of the boxes in 3D and where they should end up in each of the 2D images. And that turned out to be sufficient for us to actually apply some of the reasoning from this 3D pipeline to 2D image processing. We're a little low on time, so maybe I won't go into too many details here, but I encourage you to take a look because it was kind of interesting to go from 2D to 3D back to 2D and kind of use the lessons that we learned from processing point cloud for a pretty classic kind of image processing task. And in fact, you end up seeing in the results here, the best performance gains are in the areas of overlap between the images, which kind of makes sense because that's where knowing something about the 3D structure of your scene can really help you, right? Like if you just view multi-view object reconstruction as like a bunch of images with no relationship between them, then they can actually degrade if like there's a car that's half visible in the camera in front and then half visible in the camera on the side. But now these two things kind of constructively work together rather than just making confusion for your learning architecture. So in the time we have remaining, which is more limited than I hoped, I'll tell you a bit about our research for learning from triangle meshes, which is of course a modality that we're all very familiar with in the computer graphics domain. Right, so a triangle mesh is kind of like a point cloud, but now I have more information. Right? Now I know that the points on the point cloud are linked together in triangular structures. Also, I think the sampling is quite different, right? Like when I showed you these LiDAR scans, these are noisy, they come in very weird, irregular patterns. I think the typical triangle meshes that we approach in computer graphics don't tend to have those particular issues. So one of the kind of typical things that we do in the geometry processing world is learn features on a triangulated surface. So like, for instance, maybe we take every point on the Stanford bunny here on the left and put it into some space Rn where like maybe similar points correspond to similar parts of the object or so on. This is the sort of basic object that we work with when we're doing tasks like shape retrieval or segmentation, what have you. And one of the most popular ways to featureize a triangle mesh is to use some machinery from the world of spectral geometry. Now, if you all aren't familiar with this universe, let me give you a very short summary. So it dates back to, I think, the 1960s, 1970s, if not earlier. Actually, probably earlier. There was a particular math problem that was posed, which was, can you hear the shape of a drum? Right? And the idea here was that you've got some drum, and you don't get to look at it, right? You look away, and you knock on it. And you get to hear an audio signal. And the question is, if you hear those vibration frequencies, can you reconstruct the shape? Now, spoiler alert, the answer is no, but it turns out that those frequencies actually tell you a lot of information about curvature, scale, and so on. And so a very typical thing that we do in spectral geometry is compute vibration frequency of a 3D model, which, if you're mathematically inclined, reduces to computing the eigenvalues of the Laplace operator. This is like the second derivative matrix. And then once we have those, that already gives you an interesting feature for your shape, right? It's like a list of eigenvalues, and you can compare that to other pieces of geometry out there in the universe, and that's somehow useful, right? It's just a long vector as opposed to like this disorganized triangle mesh. Now, this is a popular technique, and a few years back, I guess several years back now, Lippmann and Bronstein had kind of an interesting idea. They noticed that people in geometry processing have proposed millions of different shape features that all have a very similar form. They all kind of, they come from like simulating waves or doing vibration frequencies or heat diffusion. All of these different things are all just functions of that list of eigenvalues. And so one of the earliest ways that people learned from triangle mesh was just to learn that function of Laplace eigenvalues. This is a one-dimensional learning problem. And it was remarkably successful for sort of early attempts at learning from triangle meshes. So a couple years back, we asked a question, which is, essentially, we're using these physical systems as a proxy for how to compare one shape to another, right? Like, how does it respond to vibration or heat propagation or what have you? But of course, there's a huge class of physical systems out there that can't be built from this one matrix, right? There's plenty of physics to be had that doesn't have to do with the Laplace operator specifically. And so we wanted to ask a broader question, which was, can we learn the sort of appropriate physical model or partial differential equation, depending on what community you're in, that sort of determines a feature that's useful for comparing shapes in a particular context. And that led us to propose an architecture that we called HodgeNet, which was built on top of a very popular piece of machinery in computer graphics, which is this area called discrete exterior calculus. Now, this is one of these fields that I think scares grad students away in computer graphics literature. But the reality is that if you cut through all the notation and you just want to think like a computer scientist, it's not so bad. That essentially what we do is we build up our matrices, like this Laplacian, out of diagonal things. That's these Hodge stars, which are like one number per vertex or edge of a triangle mesh. And these Ds, which are combinatorial. So even if you want to ignore all the fancy exterior calculus math here, the reality is that coding these is pretty straightforward. And at the end of the day, we can kind of replicate a lot of geometry processing using basically two diagonal matrices, these two stars here. And so essentially what we proposed was to make those stars learnable. So the HodgeNet architecture inputs a 3D shape. And here yellow means learnable. Everything else is just like kind of a standard calculation. And it actually constructs that Hodge Laplacian where these Hodge star matrices are the things that we learn. These are really simple features. At the end of the day, it's like one number per vertex, which is just a function of like the edges going out of that vertex. This is pretty simple stuff. And then we build up this Laplacian operator and compute its eigenvectors just like we would in standard geometry processing before deep learning was a thing. So essentially, when it comes to machine learning here, actually the thing that we're learning is quite simple. It's just a local feature on a triangle mesh built out of like a one-ring neighborhood. It looks like the kind of calculation that we would do in finite elements or things that pre-existed before machine learning became a thing. And the kind of exciting and cool thing is that this can help us achieve state-of-the-art in these machine learning from triangle mesh tasks with far fewer learnable parameters than a lot of the work that came before it. Now, the reality is that engineering this tool is a little bit tricky because of exactly the challenges I mentioned at the beginning of this talk. Essentially, we were writing down all this math being unencumbered by the fact that like sparse linear algebra and all the building blocks here are not well supported in PyTorch. So at the end of the day, we had to propose a lot of kind of custom techniques for how do you differentiate into sparse computation and so on. And I think there's a lot more exciting and cool research to be done here, both mathematically and on the engineering side. But at the end of the day, kind of an interesting side benefit of this perspective is that we ended up with a technique that's actually more scalable than past work because we couldn't run it on the graphics card. We were using like CPU-based calculation anyway, and that turned out to be, in a sense, more scalable because we weren't stuck in graphics memory and doing kind of order n squared style calculation, which you're often kind of stuck doing in the usual deep learning regime. So I think we're just about out of time. As a quick recap, essentially, I told you two quick kind of threads about what it takes to learn from a shape. We started with point cloud, and then we ended with meshes here. And notice that in both of these settings, what we tried to do was engineer machine learning techniques built from standard geometry processing operations, rather than proposing new geometry processing to fit the existing machine learning tools. And in both cases, we were able to achieve some pretty good result and still have a pipeline that looks kind of sensible to a person that was working in this field 10, 20 years ago. I think there's a lot more to be done here, and essentially having some knowledge of the domain area you're in really can bring a lot of benefit and interest and some exciting research problems to study. Of course, there's no shortage of really fun problems to study. I've given a few pointers to some of the more recent work that we've done in our group. We've studied a few computer animation problems, which presents all kinds of problems in its own right. I mean, I think just computer animation, even without machine learning, is such a challenging space that introducing some of these learnable tools apparently will crash PowerPoint. There's also some questions about whether we can take these ideas, extend them into higher dimension, and maybe study more abstract point clouds in other spaces, which appear in many different applications, and eventually to take these tools and introduce them into the interactive modeling environment that we really want to see in computer graphics world. At the end of the day, software for CAD and 3D modeling looks an awful lot like it did 10 years ago, and somehow despite this huge literature in this domain. So I think there's a lot of space here for innovation and creativity. So in any event, I really appreciate everybody's time. I don't know how much time we have for Q&A, but I'm happy to chat or find you guys during the coffee break. So thank you so much for joining me today.
Thanks, Justin. That was great. I don't know if I have to sit in this chair or not, but there's time for questions. I said we started late. Sorry?
You're the chair. You have to sit in the chair.
So we started a bit late, so I think there is certainly time for questions. And for people who are joining online, I think you know the routine for the Discord questions. I'll start by asking a question in the sense that, I mean, the very beginning of the talk, you were talking about these two sides of having, the second part being using geometric techniques in the data processing. But then in your first example, it felt like maybe some of the geometry was actually, like some of these intuitive things you would have in your geometry, notions of curvature, whatnot, they're not actually necessary. You just like feed it the raw points. So are these still interesting opportunities to, or what parts of geometry am I misinterpreting that where we can?
Totally follow your question, but maybe I'll answer the question I hope you asked, and,
okay.
And then you can tell me. No, I think there is a really fascinating question, which we worked really hard in the geometry processing community to study these really refined ideas of like curvature and differential geometry on meshes, and I think it's not super clear how well those kinds of calculations align to the practical things that we want to do on some of these domains. On the other hand, using these generic learning tools has led us into some really interesting directions. So one of the unexpected things that happened with this DGCNN architecture I mentioned for you before is it became extremely popular among particle physicists, which I know nothing about that domain, but apparently they have large four-dimensional point clouds that come from Hadron Collider or what have you. There's nothing special about that architecture that was 3D. So I don't know, on the one hand, letting your learning tool completely figure out the relevant geometric structure is a totally reasonable way to go. On the other hand, who knows if a little more knowledge of the universe can help you out. I don't know if I answered your question at all. Probably not.
I think it was. There is a. Oh yeah, Ivan. Oh.
There's one online too.
Yeah, thanks for the great talk, Justin. I was wondering how well these methods work when the quantity of data you have changes. So if I'm acquiring more and more points in my point cloud, or more edges and faces and vertices, as I'm gathering this, can these estimates be updated easily? Is there a long training process that has to happen?
That's a fantastic question, and I don't have a good answer for you. I'll tell you two things that are sort of adjacent. For one of the big themes, and I think the most popular problems to study this year, who knows next year, in the sort of machine learning plus geometry space, is to see how much of these tools which were kind of supervised can we make unsupervised or self-supervised. So specifically, to give a very concrete example, in autonomous driving, it's very easy to take an autonomous vehicle or a normal vehicle and drive around Montreal for hours and collect huge amount of point cloud data. That's not hard. What is hard is creating things like this Waymo data set where you had these. Every time I look at this data, I think oh my God, this poor person. It sat there and annotated these millions of points one by one to tell you where the humans and the cars and everything else are. And so there's this big push recently to see how much can we learn just from the structure of the data without requiring human intervention or labeling. On the other hand, I think your question was closer to what we might call online learning, where your data kind of comes to you piecewise and you want to draw some kind of inference. And that makes perfect sense in the computer graphics world. Like, for instance, in this registration problem, you could imagine like walking around an object with a camera and building up a 3D model. There's some really fantastic ideas for that, especially in kind of 3D reconstruction space. I'm guessing our yesterday's speaker would actually probably know more about that than I would. I think a lot of the architectures I talked about today are not suitable as is for that kind of interactive setting. They're not the world's most efficient computations, but there's a lot of exciting space there to kind of make it so. Both, I think, there's sort of two different challenges, right? One is learning, like figuring out the learning model, and the second is inference, right? Like even if you've just fixed your learning model, making it really efficient to evaluate is itself a challenge in geometry. Yeah.
Thanks for the talk. So my question is, how sensitive the techniques that you mentioned is to, let's say, density of your mesh, sampling density, whether it works for coarse or fine or both, kind of. That's it.
That's a fantastic question. So the question was like, how sensitive are these methods to sampling? The original DGCNN was very sensitive, right? Because it was collecting some notion of k-nearest neighbors. So if you had like at test time really dense neighborhoods and at training time really coarse ones, then the features that you're learning really don't transfer. There was a ton of follow-up work that attempted to address that issue in many kind of interesting ways, like trying to maybe estimate some underlying geometric structure. But that was a challenge in the original work. For learning from meshes, it was a little bit less so. And the reason is that essentially in this HodgeNet architecture, our sort of point was to build it in such a way that it resembled the kind of calculation you would do in finite element, like in physical simulation, right? So in principle, the same way that like your discrete Laplace operator converges to some smooth thing in the limit, by just training on meshes of many different resolution, what we found is that oftentimes, for example, we could train on meshes in one regime of resolution and test on much denser ones, or the other way around, and that a lot of the features worked okay. I'm not going to claim that this problem is solved. To my knowledge, no 3D learning architecture is like truly resolution invariant, but I think ours was a little bit more so, and the reason is that we were kind of building it from pieces that make sense in like a PDE kind of universe, right? The same way that like the cotangent Laplacian, which is so popular in geometry processing, works okay for both coarse and fine geometries. There's a lot more to be done there, for sure, there. I think sampling invariance is one of the biggest problems in this domain.
All right, one last quick question before the next part of the program. A question from Min on the Discord. Is your new work on triangle mesh learning applicable directly to watertight point clouds with sufficient sampling, considering SOTA normal estimation and implicit representations for surfaces?
Well, there's sort of three different modalities mentioned in the question here. There's triangle meshes, point clouds, and these neural implicits. And they all have interesting sampling considerations. I tend to talk too much, and I'll try not to. I guess I kind of addressed the first two, right? Like point clouds versus meshes and some of the challenges there. Of course, what's all the rage in 2022 are these neural implicit shape representations, which are also super cool. I think they're not necessarily widely used in graphics practice, which was sort of dissuaded me from studying these originally, but I'm coming around. One of the interesting opportunities is that these implicit shape representations don't have a sampling issue, right? And so actually I think you see some of the modern point cloud architectures trying to like infer a sign distance function and then do the learning on that object for exactly that reason. I don't know specifically, normal estimation and it's sort of a benchmark problem, I think, in machine learning that it's been studied to death. But I think there's a lot more to be done there, that like at the intersection of these different modalities, maybe that you can kind of use the fact that implicits are less sensitive to sampling and point clouds can be gathered from the real world and meshes have lots of detail, and maybe there's some interesting way to combine all these things. This is still kind of unexplored, and if you guys like these kinds of topics, please come hang out. I'd love to talk more.
Certainly time in the coffee break, which we've only, I think, eaten 15 minutes into.
No.
But so, hey, one more round of thanks for Justin. And next up on the program is the Dissertation Award talks.
All right, I'm just going to throw up a slide super quick. Thanks for the talk, Justin.
I think I managed to tangle myself.
Oh. All right. You can probably come up and get ready. All right, so I have the honor and privilege to present the Alan Fournier Award this year, which is given to the author of the best PhD dissertation in computer graphics from a Canadian university. And this year the award goes to Ryan Goldade. And if you've been to SIGGRAPH in recent years and you've looked at some of the videos coming out of the fluids community, you probably remember many of Ryan's works that he's published at SIGGRAPH and at Eurographics in recent years, but especially the one with the bubble coming up through the fluids. It's always memorable for me. I think that was a really cool paper that you worked on. But his dissertation, which he's going to tell us about today, is entitled Efficient Liquid Animation, New Discretizations for Spatially Adaptive Liquid Viscosity and Reduced Model, Two-Phase Bubbles, and Viscid Liquids. Sorry, I had to read that out. I couldn't memorize that one. But he has contributed significantly in the area of fluid simulation, not only in terms of the efficiency of fluid simulations with bubbles and viscosity, but also in the capabilities that we now have in simulating these types of phenomena. And just as a side note, throughout his PhD, Ryan actually worked at side effect software. So many of the methods that he's developed have now been implemented and integrated into to Houdini. I'm sure he's going to tell us more about that. Congratulations again, Ryan.
Thank you. Okay. I think this will work. Oh no. I lost the mouse. Okay. All right. Thank you. Thank you, Sheldon. That was a lovely introduction. It's a great honor to be awarded the Alain Fournier Award. Yeah, it's incredible that people even like my research at all. I'm just thankful that people appreciated it. Spent a lot of time working on it, and I got the opportunity to work with a lot of really amazing people, which I'd like to thank. I started in computer graphics, doing internship with Robert Bridson, which led to interning with Chris Voitan, and that led to a PhD with Christopher Batty, and I owe an incredible amount of thanks to him for his mentorship and his patience as papers got rejected and resubmitted, and his friendship. Then I interned at Side Effects with Jeff Late as my supervisor, and then they kept me on part-time, which allowed me to tech transfer my research into their products. I managed to run away to New Zealand for a short period and work with Ken Museth, and then as a full-time now with Reality Labs, I worked with Brendan Smith and Ladislav, and if you recognize these names, these are incredibly talented and smart people, and I'm just so fortunate to have been able to work with them. And my collaborators, Merdul, JC, Jonathan, Yipeng, which we've also worked on research, some of which has yet to be published, and other people through my travels at these various companies. And yeah, anyways, friends, family, and of course my wife, Monica Goldade, who had an incredible amount of patience during the PhD, so I owe her a lot. All right, let's get on to the talk. Okay, so let's start with why we want to do physics-based animation in the first place. So say a movie studio needs a raging fire or a big storm in one of their shots. The challenge with doing this practically is that it's probably expensive. It's likely unrepeatable. You're not going to build another building and burn it, which also means it's uncontrollable because you can't redo it with flames in a slightly different place. It's obviously dangerous, and in the case of the storm here, it may not even be possible to do. Right, so how might we do this? So we can use non-physical methods, like artist-generated methods or procedural methods, And so these are fast, they're easy for an artist to control, but they don't really scale well to large 3D scenarios, and it's hard to achieve realism in that environment. Okay, we can go all the way to CFD, where we get accuracy and realism, but it's extremely slow because they're so concerned with accuracy, and it's also uncontrollable in the sense that the turnaround time to simulate is so long that an artist can iterate rapidly to adjust the type of shot they want. Because while we want realism, we also want realism and then there's cinematic effect in movies, which can stretch beyond realism. So this puts us in the middle of computer graphics, where we're kind of our own focus here, where we want realism, but we want it to be fast, we want it to be controllable, we want to iterate on it quickly. The artists have a lot of demands that that sort of pull us in away from CFD. And we want it to be accurate, but we only want it to be accurate enough that we can achieve what we want, and we don't need it more accurate if it doesn't add visual quality. So we're going to make a lot of shortcuts in this talk. And the first one is embedded surfaces. So the idea here is that I have a really high resolution splash here that have a nice blue surface, and I want to simulate this with a lower resolution physical grid. So the physical grid would be in orange here, and if you tried to represent this with a level set, you wouldn't be able to see any of this detail. But I want the detail, I just don't want to pay for it. Okay, so let's talk about how we couple the two together. So the surface is coupled with the physical simulation through boundary conditions. So the surface tells the physics where the fluid surface is, and the physics solves for the velocity of the fluid, and it tells the surface how to move. Okay, that's how they're coupled. The challenge here is that the surface scales by the surface area, which is nice, but the physics scales by the entire volume. So if I want to double the resolution of my surface, and I want these two resolutions to match, I have to pay a significant penalty to double the resolution of the physics, and this motivates the embedded method. And there are plenty of previous work that use this approach, but it causes problems. The last example, Boyne, Hansen, and Voitan, is what we'll focus on and how they fix this problem. So if we look at a really quick example, on the left here we have a matching resolution, so we have 256 cube voxels for the simulation and the level set. On the right we have, that's right, yeah, left, right. On the right we have a lower resolution physical simulation, but a 3 times higher resolution. What is going on? Yeah, 3 times higher level set. Okay, and so immediately we can see a problem, right? So the matching resolution loses volume. Now this is level sets, and flip particles might not have this problem, but we'll stick with level sets for now and just show that we get significant volume loss. So we actually get better detail by having a higher resolution surface and a lower resolution physical simulator. Okay, so, but there's a catch. Let's just play this again so we get nice volume preservation. But as the fluid crashes down, it starts to create ripples in the embedded surface that never go away. And this is because the physics can't see this error. You can imagine ripples between the physical grids that just can't perceive this error. Okay, yeah, so back to Boyne and Hansen. So they worked on this method where they can basically detect where these errors are occurring. They build forces out of this mismatch between the surface and the pressure gradient that the physics solves for. But they still have artifacts in their results, and they also have a steep time step integration restriction that is on the order of the high resolution surface, which is not ideal. So my first research project was on improving this. So we wanted to remove the subgrid errors similar to what they're doing, but we want to use some sort of filtering method that's stable without time step restrictions. And we identified where some of their errors came from in the results. So we managed the narrow band of a level set, which I'll visualize in a future slide, and grid artifacts during advection due to interpolation. And the implementation to fix these problems is quite simple, which is the reason why we called it a practical method. And then we demonstrated this at Eurographics. Okay, so to explain the method, so if I just took an embedded surface here and I just ran some sort of filtering on it, I would get this smoother surface, but I would lose all the detail, and this is the whole point of having the embedded surface. And so we identified that in the ballistic splashing regions, you get pressure gradient magnitudes that are really low, and in the bulk fluid, you get pressure gradient magnitudes that are much higher. So we can actually do a targeted filtering. So in this case, we take a high-resolution mesh surface that we had before. We can downsample it using Laplacian smoothing, and then we can essentially just blend the level set sign distance values together using the magnitude of the pressure gradient and remove the artifacts on the surface, but retain the nice splash details. And so here's an example. So the green here is just an embedded surface without any error correction at all. And the blue example is if you use Laplacian smoothing everywhere, where like you just lose the features of the dragon immediately. And this is our method where we do this blended approach. Compared to Laplacian smoothing, we retain much more detail, similar to the embedded method. But we're able to remove errors on the surface as the simulation progresses. Okay, so the second source of error was due to ghost fluid. I'm going to really run through what ghost fluid method is here. So we have, basically we want to have zero pressure on the surface, but the surface doesn't line up to our simulation grid, so we have to do this somehow. We come up with this ghost fluid PG, where if we interpolate between the two at the surface, we get pressure equal to 0. Okay, so if we have a level set here, along the surface, we may only have grids that are very close to the surface, so it doesn't reach all the way down to PL. Now this means that we won't have an accurate sign distance value, and if we do interpolation, we're going to get bad values. So what we do is we dilate the voxels out. I mean, this is relatively straightforward with something like OpenVDB. Then we do what's called surface dilation, where we move the surface up half a voxel. This is simply so that small droplets are seen by the physical simulator. So small droplets may not be seen, so we need to do this dilation. And then once we've done that, we've basically shifted our ghost fluid pressure where we have to do the dilation again. And this matters a lot. It'll be obvious here the impact that it has. So this is our method with the improved ghost fluid. We're not using any error correction, just to make it obvious. See these stair-step artifacts that show up. If you don't do this, this was in previous work, and then this is the result of our improvements. Okay, and then the last source we identified, the last source of error we identified was advection, which basically just means advancing the surface forward. We have a black representation of the surface. It's being advected by a sparser representation of a velocity field, so you can imagine like a lower resolution physics simulation. And then on the left here, if you just use linear interpolation, you end up with these the word escapes me, but you end up with these linear patches. And then if you use cubic interpolation, you end up with a much more rounded patch. And this definitely shows up in the simulation. So in this case, we have already patch artifacts on the surface. If we use cubic interpolation, we don't have them. If we zoom in, they're really obvious in the rendering. And then our cubic interpolation, we're able to remove it. Okay, if we put it all together, this is a combined approach of the same dam break. And this is what it looked like if you didn't do anything, with errors all over the surface. And this is our approach with our error correction. Okay, so that's how you do embedded surfaces. Let's go into the next project, reduce liquids, where I essentially have been working on model reduction for various types of liquid simulation. So I briefly mentioned pressure being 0 at the surface. So this is referred to a free surface method. And we use this for all types of things like the crown splash, the ocean simulation, the viscous coiling. The idea here is that we just treat air as a massless void. And again, we're making simplifications, but we're trying to make careful simplifications. Like, we don't really need the effect of the ambient air for the ocean simulation, and you probably don't want to simulate it either, same as the viscous coiling. But there are drawbacks. For example, if you use the free surface method with this water cooler example, it would just purely pour through, because the air underneath is treated as a massless void, so it doesn't create any sort of resistance. And so we propose, instead of fully simulating the air regions, to use a constraint method, where we just have a single incompressibility constraint per air region, and then we're able to recover the glugging motion you'd expect from a water cooler. Right, and so using our constraint method only introduces a small additional cost over the free surface example, which couldn't capture the phenomena at all. Okay, so our contribution for this project was a 0 flux constraint, so this incompressibility constraint. This works well for 0 density bubbles. We don't have to simulate anything inside the bubble at all. We don't have to do advection, pressure projection, and we end up not having to have large density ratios between air and air in the liquid, which causes problems with matrix conditioning. So we found this doesn't work for our higher densities. So we developed this affine region method where we model the interior of the bubble with the affine vector field. And then we can actually use this as a general strategy to speed up even free surface simulations. And so we presented this at SIGGRAPH in 2020, and it made it into Houdini 16. So I think, if I recall, only the constraint approach made it into Houdini, but it made it there. Okay. Right, so let's explain what was going on with the water cooler example. So if we have a simulation grid that we've stamped around our liquid here, again, we're treating the air completely unsimulated. So the air imposes no resistance on the liquid, and so it just pours right through the neck because there's nothing there to stop it. But if we wanted to simulate it, one approach would be to do a two-phase method, which we extend the simulation grid into the air region, which we represent with red grids here. And if we did that, we would get the expected resistance where the water would pour through the middle and the bubbles would go up through the neck. But this is significantly more expensive because we have to simulate that entire air region below and above. Plus, like I mentioned, the density ratios makes the matrix poorly conditioned, which slows the solve time down. So these are costs that we don't want to bear if we don't have to. So this is where our constraint method came from. So the idea is that all we really want in that simulation is we want the effect of the air resisting being compressed as the liquid pours through. That's essentially all we want to capture in the phenomena, right? So we can model this by simply saying, well, we'll just say that the entire air region is incompressible, and we can do this by integrating around the boundary. And I've tried to remove as much math as I can, so there'll be some math, but there won't be a lot of math, so bear with me. Right, so the idea here is that at the air-liquid boundary, we would integrate the velocity in the normal direction, and then we would also integrate the motion of the solid boundary if the solid boundary was moving, which will show how this works in a future slide. Right, and that's how we can create that glugging effect. Oh, yeah. And then we can also use it to simulate rising bubbles in water, like this example. And in each case, each bubble is just represented by a single incompressibility constraint. We never simulate the interior at all. And we can do more complicated methods. So in this case, this red piston will push down through the tube. And because the air bubble inside has this zero net flux constraint, basically the flux that's imposed by the piston moving down will get forced on the green liquid, and this will have a chain reaction through the pipe. So we can create this cool like added distance effect as a result. And an important thing to mention here, again, we're not simulating the air at all in the pipes or in the ambient region. If you were to try and do this with a two-phase method where you simulated everything, it would be a huge expense, and it's like unclear if you would actually get simulation quality improvements as a result. And we can also compare against a two-phase. So we have a ground truth two-phase simulation. We show that our constraint method like pretty closely matches the behavior. But our method does fall apart when we go to more dense bubbles. So in this case, we have matching density between the outer liquid and the inner bubble. And we'd expect no motion at all because the densities match. But in fact, the constraint method increases. And then if we went to high densities where we'd expect the bubble to sink, we still get rising bubbles. So this constraint method is good for low densities, but it breaks down in regimes of higher densities. And there's a pretty good explanation for why. If you look at the pressure inside the bubble for low density bubbles relative to the liquid, the pressure is relatively constant. So approximating the whole region as a single constraint is a pretty good approximation. But for anything higher, it clearly is not constant, and so everything breaks down. So to attempt to correct this, we bring in the affine region idea. So if this is our constraint method where we have liquid cells on the boundary, and then the entire interior is approximated with a constraint, the affine region equivalent would now include simulated cells at the bubble boundary, where we do what's called like a two-phase, where we handle the density differences. And then the interior is then approximated by an affine vector field. And so simply, we can model the velocity anywhere inside the green region as UB, basically with a constant term and a linear term. And then all of our fluids we want to be divergence-free. We can enforce this simply by making the trace of the linear term equal to 0. And then when we do that, we can recover hydrostatic bubbles with matching densities. And for higher density bubbles, we can also get the bubbles to sink with the affine method. And this extends to the 3D case as well. And using the affine method, we get a significant performance improvement over a full two-phase solve, which ends up being almost 3 times faster. And then we said, okay, well, that's pretty cool for bubbles, but like, could we just do this for free surfaces? I mean, there's no reason why there's no reason why not. So for small bubbles, using one affine region is okay, but for large simulations like a splashing liquid in a circular container like this, it doesn't really work. And I'll show an example of that. So we basically said, well, what if we take the affine regions and make them smaller and then just pad them with simulated cells between each region? Right, so if we take a look at this tiled structure, on the left is a regular grid, which basically means every single cell is being used. For the physics, the single affine region, again, means the green part is one single region. And then the tiled is simulated cells between affine regions. And we do recover much better behavior. Let me just go back and play that again. We get much better behavior using the tiled approach than the single approach, especially where the fluid splashes back, where it's not expressive enough to represent the motion. But the tiled approach is, which is really cool. Okay, and then so this also holds up for a 3D, where we closely match the regular grid in a big splash tank like this. And likewise, we get big performance improvements. Get a 3.7x speed up over the regular grid approach. Okay, so for my last project, I worked on accelerating viscosity. So in addition to solving for pressures, which I briefly touched on but largely glossed over, I was also interested in solving viscosity. which is an important component of a fluid simulator when you want to simulate fluids like oil or honey or molasses. And you can also do artistic things here, like you can simulate melting a bunny using viscosity, where the viscosity coefficient was based on an artist-driven temperature. But there's a huge problem in doing it, and that's it's really, really slow. Like it took like 95% of the simulation time. Sorry, 95% of the simulation time was taken up by the viscosity solver, and everything else. I briefly mentioned advection, pressure projection. Anything else that's going on is only 4.5% of the time. So this is a huge, huge cost. And so using our adaptive method that we published, we were able to reduce this down by 37 hours for that melting bunny example. So it went from 50 hours to just 13 hours to solve for the viscosity. And the cool thing is that the overhead introduced by adding adaptivity is really small. As you can notice, the overhead component is minuscule. Okay, so the main contributions for this was essentially building a variational framework where we discretize the viscosity PDEs onto octrees, which required careful discretization, but we can guarantee symmetry, which allows us to use fast solvers. We showed that this works for free surface viscosity, variable viscosity, like the bunny example, and we verified that this indeed converges with analytical examples. And we show that we can achieve a 9.4x speedup in some of our examples, and then in other cases, like the bunny wire example, the regular grid approach just completely fails. So we were able to simulate at higher resolutions than you could previously. And we presented this at SIGGRAPH in 2019, and this became a feature in Houdini in 18.5. Okay, so so simulating this bunny here, regular grid method would just stuff the bunny with these magenta cells. But something we observed with viscosity is that the viscosity damps out the velocity field in the interior of the liquid. So we can approximate the behavior of the liquid with an adaptive strategy, and we don't lose much visual detail as a result. Okay, so the idea here is that we would maintain a fine layer at the surface of the liquid, so the magenta cells, and then we'd gradually coarse in from cyan to yellow to green until we have the interior of the bunny filled with these coarse cells. Right. And an interesting example here is that for like large rotation modes, which is where viscosity really shows up, we can actually achieve matching results as we introduce more and more adaptivity. So this is basically a cutaway example of a fully uniform grid in the interior, the same simulation with one level of coarsening, 2 levels, and 3 levels. So we have 4 levels of grid sizes for the green, and they all line up the same to the regular grid. So there isn't a visual trade-off here. If you want to get faster simulations, you can use this and you don't have to sacrifice the results. Right, okay, and so we can also reproduce bending and rotation modes that you'd expect in this buckling example. And again, it closely matches the regular grid. And this example was 3.8 times faster. We can also capture scripted solid interactions with the liquid velocity, or sorry, the viscous liquids. And in this example, it's 5.5 times faster. And in this case, just to give some like context here, this goes from simulating this for over 3 days down to 13 hours. So the 5.5x turns into pretty significant numbers. Right, okay. And then for this example, to really demonstrate the speed difference, we've modified the playback speed relative to the viscous solve times. So the one on the right now is done, like it's finished simulating. And the one on the left will go for another 40 seconds. And in this example, it was 9.4 times faster. And this reduced the simulation time from 26 hours down to just over 3 hours. Okay, and then finally, as I mentioned earlier, if we want to capture this thin-solid interaction of the viscous bunny, we need to have a very high resolution to do it, and the regular grid just fails to converge in the linear solve, whereas we're able to still solve this problem using our octrees. Okay, so let's wrap this up. Okay, so my research covered doing embedded systems where we're able to remove time step restrictions and artifacts present in previous work. We presented a reduced model that started from a constraint-based approach so we could capture the glugging motion that we wanted for low-density bubbles. This didn't extend to high-density regions, so we introduced the affine regions, which we were able to generalize as a strategy to speed up normal free surface fluid simulation that you would typically see. And then we also introduced an adaptive framework to discretize the viscosity PDEs that was symmetric, so we could use things like conjugate gradient. It was sparse, we proved it converged, and we got speedups of up to 9.4x. Great. Thank you.
Thanks very much, Ryan, for that great talk. By the way, I do have a plaque for you. I just have forgotten it in my office. That's
okay, no problem.
Do we have questions for Ryan? I have time for a couple of quick questions. I think Henry in the back has one.
Hello, Ryan. Congratulations. So does your work on the adaptive viscosity stuff handle examples where you have two fluids with very different viscosity, like water and honey, for example?
So yes and no. It can handle variable viscosity, but handling viscosity where you have a very sharp boundary, like those two types of fluids, I think it's an interesting problem, not one that is really explored much in the graphics community. Like, I don't think previous work solving this viscosity problem really has even addressed it, because you need to have you essentially need, your viscosity solve needs to handle that discontinuity very carefully. So you could do it, but you might see like kind of blurred out behavior between the two fluids that might not look exactly right. If you simulate it at high enough resolution, it might just be good enough. Yeah, I don't know, I haven't explored it, but I think it's, I think doing it correctly is a challenge.
Okay, thank you very much.
I'm gonna ask a quick question. So you graduated from the University of Waterloo. That's where you did your PhD. So what are you doing these days? What's next for Ryan Goldade?
I haven't done fluids since. Yeah, so I'm at Reality Labs Research now in Zurich, and we're working on biomechanical human faces. The idea is that we want to build strong physical priors to train machine learning, essentially, because everything at Meta now is metaverse, right? So there's a strong emphasis on being able to have like physically realistic avatars in virtual space, which inevitably have to use a headset. But if we have strong priors, we can train the network faster with less data or less good, lower quality data. And that's what I'm working on now.
Cool. And if you saw our first keynote earlier the week, you know that faces are the highest priority.
Right.
Right? So.
Yeah, I've read a lot of his work trying to figure out how to do this. Yeah.
Great. Well, I think we're running really tight on time, so I'm just going to say if you have more questions or want to discuss with Ryan about his thesis during the coffee break that we have coming up, you can do that. But Ryan, congratulations again on this excellent work. We have another award talk coming up, but in the meantime, I have 3 phones here. If you're missing a phone, please come get your phone.
You guys switch over to the computer display, please. Yep, no problem. Let's see. What do we have here? Okay. Okay, our next award is the Bill Buxton Award for a dissertation, a PhD dissertation in human-computer interaction. And this year it goes to Xin Tong, and she is not unable to be with us, unfortunately. She's stuck in Shanghai, and they won't even let her out of her apartment, never mind the country. So she received her PhD from Simon Fraser University and has done a postdoc at Stanford in the Pervasive Wellbeing Tech Lab. And currently she's an assistant professor in computation and design at Duke, and I'm not sure if I'm going to pronounce this right, Kunshan University in Shanghai. So she can't go to her office either. So her research focus involves designing, developing, and evaluating systems for vulnerable people, and that's near and dear to my heart. And she's published widely in Chi, and I'm sure if you attend Chi, you would have seen her work. And there is an interesting factoid that we need to know. She has won the Youth Fashion Award for the Tsinghua Italy Youth Fashion Competition. And I don't know what that means. But Milan maybe is in her next career. All right. I think we have her presenting, and we'll see her.
My name is Xin. Today, my presentation topic is bodily resonance, exploring the effects of virtual embodiment on pain modulation and the fostering of empathy towards pain sufferers. In this presentation, I'll first introduce the research background and motivation. And then I'll talk about 2 trajectories of my research. The first trajectory focuses on embodiment, VR, and pain. The second one focuses on empathy. Finally, I'll summarize my research and discuss a potential framework for future studies. Let's start with pain. The International Association for the Study of Pain defined pain as an unpleasant sensory and emotional experience. I decided to focus on chronic pain because globally, chronic pain affects around 20% of the population and persists longer than 3 months. Chronic pain is hard to be cured and causes huge economic burdens. Patients not only experience pain, stress, depression, but also suffer from social stigma and isolation. Therefore, we need ways to support the self-modulation of chronic pain and to foster the public's awareness and understanding toward this population. Gatchel et al. Viewed pain through a biopsychosocial model, which suggests that pain results from dynamic interactions among biological, psychological, and social factors. In my dissertation, I adopted the biopsychosocial model as the underlying theory for understanding the modulation process and potential impacts for chronic pain. What does living with chronic pain feel like? Perhaps most of us don't belong to the 20% chronic pain population. So let me introduce the situations of some of my participants. The patient on the left suffered from phantom limb pain for over 20 years. Almost every 10 to 30 minutes, he experiences bursts of pain that feel as if his brain exploded. He quit his job and also developed depression and anxiety symptoms. Now, he rarely meets anyone besides his caregiver and lives an isolated life. To participate in my study, he took a 3-hour flight and stayed in a new city for 1 month with his wife, just because he wants to try out possibilities that may help his situation. Similarly, on the right, this amputee patient spent 4 hours with his caregiver in train for a single trip to the lab. Can you imagine this is the life for most of them? We can see that having chronic pain sufferers affects every aspect of patient's life, and the biopsychosocial model comprehensively depicted that. To address the 3 aspects of challenges chronic pain patients face, I took a holistic approach and included 2 research trajectories that tackle the pain management problem and social stigma problem. In the first trajectory, I put patients in a healthy avatar to reduce their pain levels. I conducted 1 systematic literature review and 3 studies with different pain patients to understand how embodied approach affects pain. In the second research trajectory, opposite to the pain research, I put healthy people in an unhealthy, painful avatar with a goal to explore how embodied VR can foster empathy towards chronic pain sufferers. This path includes 3 iterations of a proof of concept VR game named As If, and I evaluated each round of iteration. So you may ask, why virtual reality and sense of embodiment? Why study them? VR is an interactive simulated environment that provides multisensory feedback. Users interact with VR, seeing an environment or interacting with virtual objects. Users then receive multisensory feedback from VR and have a presence illusion in the VR world. The illusions could be categorized into 4 types: self-embodiment illusion, the illusion of being in place, the illusion of physical interaction and social communication. Presence creates perceptual illusions that alter one's cognition and behaviors in many profound ways. Since embodiment is the focus of my research, so I'll elaborate on embodiment next. Virtual embodiment is the ensemble of sensations that arise in conjunction with being inside, having, and controlling a body. Virtual embodiment includes 3 critical subcomponents: ownership, agency, and self-location. Sense of ownership refers to one's self-attribution of a body. Sense of agency refers to the sense of having global motor control over the body. Sense of self-location refers to one's spatial experience of being inside a body. Among all non-pharmacological treatments for pain, immersive VR has shown outstanding promises for pain management. So how does VR work for pain modulation? Researchers primarily studied 2 potential mechanisms: distraction and embodiment. From findings with acute pain patients, researchers like Hunter Hoffman viewed VR as a whole and hypothesized that VR could compete with pain for limited cognitive resources and thus reduce pain levels. In other words, the authors thought that VR could draw the patient's focal spotlight into a virtual world, providing an intense sense of immersion and shifting the patient's awareness away from their pain. Virtual embodiment is another emerging theory. Findings show that merely seeing a virtual body can have an analgesic effect on healthy people's induced pain. Viewing virtual body with different appearance and sensory features may adapt people's perception of pain. For instance, Zanini et al. Studied how virtual arms' shape and motion states affected embodiment and participants' hip pain perception. However, most studies primarily evaluated the effect of ownership and on pain. Agency, another critical component of embodiment, has not been adequately studied. More importantly, most of the studies were conducted with healthy people under induced pain, and few looked at chronic pain. So I conducted 3 studies with 3 different populations. My specific research questions are, how do varying appearance and motion conditions of virtual arms affect pain? And how do ownership and agency correlate to pain reduction? I'll mainly talk about my other studies and won't spend much time here. Briefly, in study 1, I wanted to validate how virtual embodiment may affect induced pain in healthy people and focused on the senses of both ownership and agency. This was the starting point for me to set up the VR and pain research. In study 1, I recruited 18 healthy participants in a within subjects study. All participants saw 3 visual conditions in VR, a control condition with no virtual body, a static arm condition where participants saw motionless arms, and a synced arm condition where arms move synchronously with the real ones. Both the static and synced conditions had significantly lower pain ratings than the control condition. However, there is no significant differences between the static and the synced condition. Participants also reported higher levels of agency and ownership in the synced condition than the static condition. Ownership and agency did not correlate to pain. In short, this study revealed that although the motion factor affected ownership and agency, it did not have an effect on hip pain. But how would this be different for patients' pain? Therefore, in study 2, I recruited 12 complex regional pain syndrome (CRPS) pain patients. CRPS patients suffer from limb pain usually after an injury. They can feel great pain that's from something as mild as a touch. Study 2 implemented both appearance and motion factors and explored their effects on CRPS patients' pain. I compared 5 conditions in a within subject study, including a control condition, the static tube, the static arm, the synced tube, and the synced arm conditions. Here, you can see that pain was significantly reduced in all 4 experimental conditions compared to the control condition. We also found that appearance had a significant effect on pain reduction. Abstract tubes had better analgesic effect than the arms. However, motion factor did not affect pain significantly. Overall, appearance and motion affected ownership. Patients reported significantly higher ownership in the arm condition than the tube ones, and higher ownership in the synced conditions than the static ones. They also reported significantly higher agency in the synced condition than the static condition, and appearance did not affect agency. Interestingly, the results showed a positive correlation between ownership and CRPS pain ratings. In other words, the less realistic the virtual arms were, the better pain relief CRPS patients felt. So after CRPS patients, I moved on to study phantom limb pain PLP patients in the third study. Treating phantom limb pain is a well-known challenge. Using virtual reality for phantom limb pain is a more popular topic than for CRPS pain. So there are some existing studies, and I firstly conducted a systematic literature review to understand the landscape. In total, I identified 22 papers and found that ownership and agency were in general under-investigated in all of the studies. So I recruited 5 phantom limb pain patients for longitudinal study, and participants experienced 2 motor tasks during each intervention for 4 to 6 weeks. In the video, we can see that the patients inhibited a virtual body. The movements of their intact limb were mirrored to both virtual limbs. We can see that the phantom limb pain patient can adapt to the virtual reality tasks pretty well. Surprisingly, in the post-study interviews, 3 participants spontaneously stated that they experienced dreams where their arms moved again without pain. Results also showed that pain readings reduced both before and after one session, and also across all sessions. Further, we found that comparing the first session to the last session, sense of ownership and agency improved a lot for all participants. These 3 studies also have limitations. Study 2 and 3 have a small sample size due to difficulty in recruiting patients. Ownership and agency's measurements are explicit subjective ratings, and future research could add on implicit behavioral tests. Motion and appearance can be tested on continuous levels, then the 2 discrete levels studied here in study 1 and 2. Also, pain types are limited to hip pain, phantom limb pain, and CRPS, and may not be generalizable to other types of pain. To answer my first question, how do virtual arms appearance and motion affect pain? In all 3 studies, I found that virtual reality conditions with arms significantly reduced pain for 3 groups of populations, regardless of the pain types, appearance, or movement conditions. Both study 1 and 2 showed that the sync condition did not reduce pain than the static ones. Interestingly, in study 2, findings suggested that CRPS patients experienced less pain in the tubes than the arms. To answer my second research question about the correlation between ownership and pain and between agency and pain, I did not find any correlation between them, but I found a positive correlation between ownership and pain. In other words, the higher ownership CRPS patients felt, the more pain they perceived. All right, that concludes my VR and pain research. Next, let's move on to the second trajectory about virtual reality and empathy. So from multiple definitions of empathy, we found that empathy is not only a personality trait, but also a kind of social skill that one can develop. Empathy helps build social connections with others and supports pro-social behavior. In my dissertation, I adopted a multi-component approach to define empathy from 3 perspectives: cognitive empathy, also called perspective taking, emotional empathy, also called affective empathy, and finally, physical empathy. While being called the ultimate empathy machine, VR embodies people into different avatars to foster empathy and reduce biases, such as racial bias, gender bias, age bias, or sexual harassment. For instance, embodying participants in a dark-skinned avatar from the first-person perspective led to reduced implicit racial bias, as the picture shows here. I aim to explore whether embodying healthy people into an unhealthy, painful avatar could foster their understanding for pain sufferers. Specifically, my questions are to understand if the embodied VR can effectively foster empathy towards pain sufferers and how, and if embodiment correlates with empathy levels. In the initial version, through puzzle-solving tasks, participants experienced a restricted range of motion and swollen right arms in an abstract background. Participants viewed the game from a third-person perspective. We implemented restricted movements because chronic pain patients usually have mobility issue and a limited range of motion. From a pilot test, we found that although participants perceived the restricted movement and visual effect as a frustrated, painful experience, they did not get the reasoning behind it and were confused about the game. So, in the second iteration, we implemented a story and embodied the participants as a chronic pain patient. In the narrative, participants need to bake a birthday cake for her beloved granddaughter while feeling uncomfortable. The tasks were still puzzle solving, but we mapped the puzzles to a set of cooking actions. So let's take a look at the game together. Participants saw the general idea of as if works, and they felt the story was compelling. However, participants still reported they felt puzzle solving did not make too much sense when one could directly manipulate the objects in virtuality. They also suggested changing from the third person to the first person perspective to build more embodied connection. Therefore, we iterated the third version, where participants can directly manipulate objects in the kitchen and bake the cake from first person perspective. We then conducted another round of testing with different participants in before-after study design and measured their empathy and embodiment levels before and after the VR intervention. Overall, participants thought that the performing daily tasks, activities with motion challenges and pain visuals in VR
understand or don't care enough to try to better
made them think more about how life could be like for chronic pain sufferers in real life. Well, interestingly, one participant whose skin color differs from the avatars reported that they felt disembodied with the virtual avatar because of its divergent characteristics. However, the restricted range of motion brought confusion for a small portion of participants who considered it to be technical difficulties. I found improved empathy levels from both the adapted empathy scale and willingness to help scales. Moreover, the VR experiences also affected participants' emotions. Participants experienced a medium to slightly strong level of body ownership and agency over the virtual avatar. Although I didn't find any correlations between ownership and empathy, or between agency and empathy, I observed positive correlation between willingness to help and kindness subscale. The limitations of this study are twofold. I only conducted a preliminary in-lab study using questionnaires and interviews to evaluate changes in empathy, and no real-life assessment has been implemented. There is also no control group of follow-up studies. But to answer the research question, when experienced the current design of as if healthy participants could take a better perspective of a chronic pain patient through visual features in VR, such as the red flashes, fisheye camera effect, and swollen arms. However, some of the participants treat restricting range of motion as technical issues. The narrative and self-talk audio worked well for participants, and the first-person perspective also improved their experience. At the end, I'd like to summarize my studies and discuss future work based on an embedded VR framework I proposed earlier. To recap, in my first research trajectory, I investigated the effect of appearance and motion factors on embodied and pain. The key findings are: seeing virtual arms can significantly reduce pain. Motion did not affect pain. Realistic arms induce higher ownership but more pain than the tube conditions. In my second research trajectory, I studied whether embedded into a painful, unhealthy avatar can foster empathy toward chronic pain sufferers. The takeaways are: appearance features works as painful visual indicators. Restricting virtual arms' range of motion can be perceived as technical issues. The narrative and self-talk strengthen perspective taking. By putting pain patients in a healthy body, we focus on embodiment illusions effect, but we did not touch on the other three types of illusions. Similarly, by letting healthy people experience chronic pain patients' life, we focus on embodiment effects on empathy. People's experience the other three illusions through the narrative components of as if. This dissertation mainly focus was to understand the embodiment effects on pain modulation and empathy generation. In other words, explored the broader questions of virtual embodiment. Can a real body resonate with a virtual body? So the brain can believe what the virtual body sees and make sense of it, leading to cognitive and affective changes. If so, how do such changes happen? And what are the impacting design factors? Further, how will the other three types of presence illusions contribute to the bodily resonance? This framework here is a starting point for a systematic investigation of how embodied VR affects pain and empathy, and can also inspire future research. For VR and pain trajectory, besides exploring the other three illusions and the relationship with VR environments and perceptions of cognition, future researchers should also recruit a larger sample size and include people with more types of chronic pain. The manipulation of ownership and agency could be carried out in varied ways and measured differently. Further, future research can compare the effect of an interactive VR environment, like Snow World, with a virtual body and without it. For VR and empathy trajectory, a control study with a control condition, such as watching a video or reading a story, and follow-up behavioral tests should be arranged. Besides visual, motor, and audio, tactile sensations can also be further explored. This work conducted 3 studies and 1 literature review to examine how embodied VR affected pain in people with different types of pain, and also studied relationships between virtual embodiment and pain. I also developed 3 iterations of as if and research studies to evaluate it, which aim to understand how embodied VR can foster empathy towards chronic pain sufferers. We proposed design recommendations for the avatar's appearances and motion stats for pain management research and applications. And I also proposed a potential conceptual design framework as the starting point for developing embodied VR in future research. This work takes a patient-centered approach in an interdisciplinary research context and can potentially create great benefits to chronic pain patients. That's the end for my presentation today. Here, I want to express my great gratitude to Graphics Interface 2022 conference and also to the Bill Buxton Fund for this dissertation award. Thank you. I also want to thank my supervisors and everyone here in this list, without whom my dissertation would not happen. Thank you, everyone.
Okay, thank you, Shin. And I'm imagining it's very late or early, like the sun is rising in your area, so thank you for being up so early for us. So do we have
Thank you
some
both.
questions?
Thank you for having me. Yeah, thank you for having me a lot.
I have a couple of questions. This is a tricky area. People with pain, chronic pain, tend to do a lot of different things to try and not be in pain. That involves drugs and sitting on mountains in Peru and whatever, everything in between. Do you think perhaps that this was an artifact of that? And the follow-up is really important. How long does this last? Because it's often, it's not about getting rid of your pain, but actually trying to manage it better.
Thank you for this great question. That's actually something I wanted to figure out in the past while doing this dissertation research. So for some of the VR and pain work, I actually was able to follow up on the phantom limb pain patients and see how it works for them, because they expressed great effectiveness during the longitudinal study. When I caught bike around 2 to 3 months after, some of them still have occasional analgesic effects, and they still remember what was being done in the study. While the study has been pretty short, and it only they only came in for once or twice per week, and it has this profound impacts after 1 or 2 months. So I'd assume if they can get it on a regular basis, it may give them better support. But on the other hand, I also agree there might be some potential novelty effect for some of them. This is something that requires further testing, and it's really important to understand, to shed light on future work.
I'm going to take it. Oh, yes. Go ahead.
Hi, Zin. How are you? Thank you for your presentation. I have a very small question in terms of, did you see or did you observe any discomfort using VR with your participants, like secondary effects, like there may be a relief from pain, but there may be other discomfort or other issues which may be added due to use of VR? Thank you.
Thank you for this great question. So that's also an important one to consider while designing the virtual reality environment as well as the study protocols, which is to not induce adverse effect, but trying to actually strengthen the potential benefits of it. Because of some people, especially older adults, patients, sometimes they're older adults, and then I was trying to for some of the environment, you guys see that there isn't fast motion. There isn't more complicated, destructive environment as in the background. So those are some of the tips I was trying to trying to avoid making people feel motion sickness in the environment. But for the because I mostly had a small sample size there, and for most of the participants, I didn't observe very extreme or severe adverse effect. It worked well, but I did know that some of them they have this hypertension responses while wearing this head-mounted display, and they may not be able to use it. So this would depending on each person's their experiences. But from the design aspects, we could implement certain tips to avoid the problem.
Okay, I'm going to get the last question because we're all very curious about this fashion award. So maybe you could just What is that? What did you do to get a fashion award?
Yeah, sure. It's very also surprised. Something surprised me as well. So after graduating, I kind of explored several other different research projects, and I did this human-plant interaction project with one of my collaborator. We actually developed a tangible wearable interface, which people can wear. It's like an inflatable wearable dress that can communicate with the plants. The plants breathe. So by detecting carbon dioxide and the oxygen released by plants, we're trying to imply that in the wearable dress. So we actually did something for the HCI domain, trying to explore the relationships between human and nature. But later on, when this opportunity of the award comes, and we decided to submit our wearable dress to this fashion competition, and very fortunate, we also won the award. So there's some surprised side effects from HCI work, I guess.
All right, well, thank you very much, and thank you for letting us know about your dress. Okay, congratulations on your award, and thank you so much for being with us far away in Shanghai.
Thank you,
Thank you, everybody. And I think your plaque is on the way. I think we now have a short break. 10 minutes. Okay, that's it. Come back. Okay.
Hi. Okay, welcome back, everybody, from that short break. We're nearing the end of the conference, but we still have some really two awesome talks in store for you. We left the best for last, and of course, I mean the best papers of the conference. And if you've attended GI before, you know that at GI, the best papers are awarded something called the Sweeney Award. The Sweeney Award is in memory of Michael Sweeney. It's awarded each year to the top papers at the conference, authored by a student author. And the first paper that we're going to see right now, it's one of the graphics papers, has been awarded to Niranjan, I'm going to mess this up, I know, Kalyana Sundaram. Okay, good. From Clemson University. And his co-authors are Damien Romer and Victor Zorden, who are also here today in the audience. And Niranjan is going to present his award-winning paper on acceleration skinning, kinematics-driven cartoon effects for articulated characters. Congratulations, Niranjan, on this excellent paper.
Thank you, Sheldon. It's an honor. Oh, screen sharing. Wonderful. Okay, cool. Hi, everyone. My name is Niranjan, and thank you, Sheldon, for the wonderful introduction. Before I begin, I just want to say what an honor this is to be receiving this award, and I definitely couldn't have done it without my two mentors here in the audience, Victor and Damien. Thank you so much. I'm forever grateful. All right, let's begin. So, I want to do things a little differently today for this presentation, because I'm not standing in front of you here as a researcher. Instead, I'd like to give this talk as an artist. I recently graduated with a master's in digital production arts from Clemson University. And this is an interesting, very unique curriculum that blends art and technology in a fun way. So while I was training to become a better artist and working on my craft as an animator, I got very interested in how, learning how all of this works under the box, under the hood, going through the techniques and learning the, computer graphics side of it. And that's how I transitioned into research. So today, I want to invite you all to go on this journey with me to share the story of acceleration skinning. So it all started with just me in my apartment watching some cartoons, as we all do. I really love the old black and white cartoons from the 1930s, 40s, 50s. We're talking Tom and Jerry, Popeye, Mickey Mouse. This is a very fun time period in animation. And specifically, I want to focus on a couple things here. We all know that Walt Disney Studios is one of the greatest pioneers of traditional animation. And they had a group of 9 prolific animators who revolutionized this medium, who they endearingly titled the 9 Old Men. And these 9 old men, along with many other wonderful artists, came up with a set of 12 fundamental principles of animation. Now, these are so iconic principles that, they've been around since like the 1920s and 30s, but they're still taught at university and at workshops today, because if you want to be an animator, you have to know them, and you have to use them in pretty much everything that you make. So one of the most famous examples of this, of one of these principles, squash and stretch. You don't have to be in animation to know how important squash and stretch is. The clip that you see here playing is from a style of animation called rubber hose animation. And it was really famous during this time period of like the 30s and 40s. Particularly, the reason I love it so much is if you look at the arms, it feels like there's no joints inside them. There's no skeleton. It's just loose hanging flesh that wobbles around along with the rest of the body. So this is the main trait of rubber hose animation. And I just love how it looks. So what's important for rubber hose animation? Well, today I want to focus specifically on one of the 12 principles of animation called follow-through. So one day when at Walt Disney Studios they were working on a cartoon, and Walt wasn't feeling particularly happy with how some of the things were moving. Well, actually, he wasn't happy with how they were coming to a stop. So he famously said the quote, "Things don't stop all at once, guys. First there's one part, and then another." This statement embodies the philosophy behind follow-through. So it eventually, became important enough so that they included it as one of the fundamental principles of animation. So what is follow-through? Well, if you look at the example of the animation clip playing here, you can see that this guy's head moves. He's got an antenna, and the antenna kind of moves along with it and sways along. It wobbles, but there's no, it's like, okay, the main body moves first, and then the flower is sort of an appendage that sways along with it. It drags behind first, then overshoots, and then comes to a rest. And this dragging and overshooting are the two kind of aspects or phases that go hand in hand to create this iconic effect. So, what I wanted to do with research was the grand challenge: how do we support artists in creating these exciting effects in 3D? Well, it felt like a lot to chew on, so why not break it into bite-sized pieces? Before getting to the final approaches, we need to understand, if we're doing this in 3D, what's the standard pipeline for doing 3D work? Because we want to know, we don't want to reinvent the wheel, right? We want to find the most optimal solution to get this done. So the standard pipeline for 3D, in general, when you're discussing filmmaking, which includes animation, of course, the entire process can be broken down into 3 primary steps. There's pre-production, which involves coming up with the concepts, ideas, stories. There's production, which is, doing the animation, getting the renders. And then there's post-production, which involves cleaning up, final polishing, editing, things like that. So specifically, when we're talking about 3D character animation, the production pipeline fundamentally involves modeling, where you create the character, rigging, where you create a skeleton setup for the character, skinning, where you define or map the character mesh to the skeleton, so that when the skeleton moves, the character gets deformed with it. Keyframe animation, which is what you see on screen, where an animator can go in and define different poses for the character over time. And finally, deformation effects to add a bit of flair to the top of it. And specifically, I want to focus a bit more on skinning, because that's what the paper's about. So in a standard pipeline, we typically use what's called linear blend skinning, which is where when a joint moves, the vertices associated with it deform and move along with it. I'll touch on this a bit more as we go on. Digging deeper into deformation effects, there are fundamentally, at a high level, 2 different ways to approach the deformation effects. One is with physically based simulation, which I'm sure all of us are familiar with, and the other is procedural effects. So, simulations. Simulations are wonderful. They give you so much detail, so much detail. There's such rich effects, but it takes a long time to compute. You have to put in your initial parameters, let the simulations run, and it really limits what an artist can do because of how cumbersome it is to control. You're defining all of your material properties in terms of stiffness or friction. As an artist, I would prefer to work with more artistic terms rather than scientific terms. And I'm sure we all attended the keynote talk on graphics earlier in the conference, and it's great to see, hear about Ziva and all the wonderful advancements that they're making in this field. It's exciting. Exciting stuff. Moving on to procedural deformation effects. This is kind of the standard approach in the industry right now. If you're opening up Maya and you want to get some procedural effects going, well, there are some nonlinear deformers that you can use and manipulate to create the effects. And it's highly controllable. You can see from the video playing right now just how easy it is to go in and manipulate all of the tiny details that you want. But at the same time, it's all manual. None of it is automated. This is essentially how animators work. You have a graph, you go in, you add keyframes, you modify how the keyframes, or you modify the values of the keyframes and the interpolation between them to define and tweak the tiniest of details about how everything fits together and moves. And it's great because it's very low level. You can't possibly get more control than that. But at the same time, everything is manual. There has to be some better way to do this. Well, we looked into it, and there were some interesting kinematic approaches used in the middle ground, but surprisingly, there weren't a lot of effects. So this is, for example, from one of the research papers that we found, where they tried to curve the elbow. You can see how rounded the figure on the right is compared to the figure on the left. And it was a very fascinating paper, but the effect was very localized. I'm getting ahead of myself. We'll go into those details later. So, what's our objective here? Well, we wanted to create some stylized deformation effects. And there's a big old laundry list of effects that you can see on the slides. We wanted to do this preferably in real time with not too much input from an animator. We wanted it to be sort of semi-automated, but at the same time, we wanted to keep the animator in control. We're not trying to replace simulations. We wanted to create an artist-driven tool. So we worked on velocity skinning. And I know technically the talk is called acceleration skinning, but these two works are so intertwined with each other that we can't talk about one without talking about the other. So I want to take a minute to introduce you guys to velocity skinning. So this is our recent technique for cartoon-like deformation. And you can see from the clip playing that we do have an interactive interface that lets users get in, grab a joint, and move it around, and you can see the deformation being applied in real time. You can see the mesh is basically getting dragged and rotated behind the joint. So this is not a special rig in any way, shape, or form. It's just a run-of-the-mill giraffe rig that we found and plugged it into our system, and here's the result. So it works with pre-existing linear blend skinning rigs. So how does velocity skinning? Okay, the supported effects so far right now, we have two deformers. You can create squash and stretch, which is parametrized using a scale matrix, and a drag deformer, which is parametrized with a rotation matrix. Again, both velocity and acceleration skinning are more like generic frameworks that let you go in and create or define your own deformers in any way, shape, or form. We simply implemented these two deformers for our tests and moved on. So let's get under the hood. How does velocity skinning work? Well, to understand that, let's take a deeper look at linear blend skinning. So for those of you who are unfamiliar, linear blend skinning is the most widely used technique for character animation. It's where you start off when you rig a character, and it's essentially taking a skeletal hierarchy and looping through the joints, summing it, and we sum the position that we obtain from rigid skinning. So if I move my elbow and I have a vertex on this shoulder right here, how does that move when I'm moving my arm? This is essentially what we compute, or what is computed in PJ. This is multiplied by a skinning weight. Skinning weights are kind of like a blend in case you won't have vertices, for example, on my elbow. If I'm going to move my elbow or bend my elbow, is this point affected by this bone or by this bone or by a combination of both? This is what's defined in the skinning weights. And these weights are readily available on all run-of-the-mill rigs. You can't have a linear blend skinning rig without these values. So what we did with velocity skinning was take all of this and integrate it with respect to time. So in place of the position, in place of PJ, or the position of rigid skinning, we now have the local velocity instead of position. But this velocity isn't the net velocity or the final velocity, it's just the velocity that's relative to the joint in question. We also have, instead of these skinning weights, what we call kinematic weights. Now these weights, it's just a very mathematical reformulation of what's happening with the skinning weights. And the intuition behind it is, if I'm moving a certain joint, like let's say my shoulder, how does that affect other joints down the hierarchy? How does that affect my elbow? How does that affect my wrist? How does that affect my fingers? The kinematic weights are just a mechanism of keeping track of all of these things. So at the end of doing all of this, what we're left with is the velocity on a per vertex basis. But we don't want the velocity. What are we trying to do here? We're trying to define a deformer. So at some point, you have to go in and define how do you change this vertex? Where do I want this vertex to go? So what we do is take the velocity, and somehow we need to convert it into a deformation function. So our approach to doing this is to just define our own abstract function, which we call psi. And as a parameter, we use velocity. Now this function can do whatever you want it to do, just that the input parameter is velocity. So what do we want to do with it? Well, this is where we have the results of squash and stretch and drag. These are different deformation functions that you can define. And finally, what we end up with is the displacement of a vertex, or where does this vertex move? So let's take a look at the drag deformer, which is, it's one of the deformers that I love the most. It's one of the deformers that I use the most. Oop, sorry, skipping ahead there. This is our deformation function that we defined for drag. All we're doing is, if we have let's say I have my arm here and I'm rotating my elbow, right? So my elbow is rotating up. We want this deformer to simply push the vertices of my mesh in the opposite direction. And we do this with a simple rotation matrix that is parametrized using angular velocity omega. And of course, it wouldn't be a graphics talk unless there were pretty pictures. So here are some of our results. We found a Cthulhu model with 1.5 million, okay, cool. We found a model with 1.5 million polygons on it, and we took our velocity skinning system, wrote a GPU implementation for this particular deformation function, and here is actually, here's a video of how it runs, and it's running at 35 frames per second. So another test that we did to show how scalable it is, we had a field of 5,200 cows running at about 45 frames per second. I don't have stats on how many vertices or quads that is, but I mean, it's 5,500 cows, it's gotta be sizable, right? So this clip is actually Damien on his computer selecting random joints and rotating the hell out of the monster. Moving on, we didn't want to stop there. You have velocity, why stop? Let's go on with acceleration. So we take the velocity of each vertex, we differentiate it again with respect to time, and we have the contribution of acceleration localized to each joint. Okay, wonderful. Next step, what do we need to do? Well, we need to create more deformation functions out of it. We pass in, now instead of sticking with velocity, we also have acceleration as another parameter to our deformation function. So before going forward, I just want to recap some terms in basic physics. We have omega is angular velocity. We have angular acceleration alpha. So when dealing with velocity, usually this is enough. When moving into acceleration, we're dealing with more terms, specifically when dealing with rotational motion. We have terms of centripetal and tangential acceleration. So to recap high school physics, if you have a body moving or rotating in a circle fixed about a central point, there's going to be tangential acceleration, which acts in a direction that's tangential to the radius. And we have centripetal acceleration, which is acceleration that acts inward along the radius. And these are things that we had to keep in mind when moving forward to define our own functions. So why do we need acceleration skinning? Velocity skinning was great, right? Well, the thing is, we're trying to model follow-through. And by nature, velocity skinning, when you have a skeleton that is about to come to rest, the velocity is slowly dropping off to zero. And at this stage, you don't have any deformation because there is no longer a velocity. So your input parameter just boils down to zero. But with acceleration skinning, when you have a drop in velocity, you still have a deceleration value. So we can capitalize on this to keep deforming the mesh during this phase. So if you look at the clip here on the left, you can see that the flower's bending, the skeleton comes to rest, and the flower just eases into a stop. But the one on the right, even after the skeleton comes to rest, it keeps moving forward and then gets back to settling at the center rest position. And this is the effect that we wanted to create and capture. So how does this exactly work? Well, this is the behavior of or relation between omega or velocity and acceleration alpha. So if you notice, look at the graph, there is the first highlighted section you see is what is essentially the speed up phase where the flower is picking up speed and moving. And at this point, the velocity is increasing, the acceleration is also increasing. At the slowdown phase, the velocity is decreasing and we have acceleration kind of changes direction. So we have a deceleration value going on. And the trick, the hook here with this observation is that if you notice the direction of omega and alpha, when they speed up, both of these values are aligned, they're in the same direction. And when the flower is slowing down, they're in opposite directions. And this gives us an approach or a hook that we can use to define our own interesting deformers. So those were just the overall concepts that we were using in this project. Now let's get down and dirty with 3 specific deformers that we wrote for this framework. The first one, follow-through. Going back, this is what we wanted to create, right? Well, it turns out we can take the drag deformer that we wrote for velocity skinning, and instead of inputting omega or velocity into that equation, you just plug in acceleration, and this is the result that you get. Pretty cool, right? But why stop there? Moving forward, the issue, or not really an issue, but one of the quirks that we found with that was we can't independently control how much deformation occurs when at the speed up phase versus the slowdown phase. So what we decided to do then was create a mechanism to separate these two. And we do that using what we call a smooth indicator function. That's a lot of confusing math, so let me break it down for you. What all this is doing is comparing the directionality of velocity and acceleration. If they're pointing in the same direction, it's drag, or the speed up phase. If they're pointing in opposite directions, oh, sorry, I misspoke. If they're aligned, it is the speed up phase. If they're pointing in opposite directions, it's the slowdown phase. So using this, we now have the ability to separate these two phases, and this gives animators a lot more control over how the final product looks, because we can separate them and then combine it back together to see what you have here. Moving on to the next deformer. This is actually a really fun one, because it was, well, we built this framework, we got follow through. Well, we have to do something more with it, right? You don't want it to be a one-trick pony. So you ever noticed in a pizzeria how when the chef is cooking, they knead the dough and then they toss it up in the air with just a flick of their wrist and the dough just expands? What if we can capture something like that with this framework, with this system? So scientifically, what's going on there? Well, when the chef is flicking their wrists, they're inducing acceleration into this dough, and that's causing it to expand out. Well, we know from math that centripetal acceleration exists when you have rotational motion, but this acceleration acts inwards. We want the dough, we know the dough goes outward, right? So this, instead of centripetal acceleration, is just a centrifugal effect. So what we did is take the equation for centripetal acceleration, we negate it to switch the direction, and then we add a single user controllable parameter to control how intense we want the effect to be, and voila. We have a very stretchy flower, which we call centrifugal stretch effect. And last, but our final deformer for this talk is a centrifugal lift deformer. So now that we have rotational motion and we have mesh that we can stretch, what more can we do with it? Well, we wanted to try and capture the appearance of twirling cloth. Now, how is this very different from the pizza? Well, for one, cloth doesn't stretch out. It just kind of lifts when you twirl, right? So our approach to doing this was to prevent any displacement along the tangent plane, so we stop the mesh from stretching, but instead we move the vertices along their normal direction independently, and this creates the lifting effect. When we were doing experiments with this, we found that it was a lot easier to perform this deformation on a simple conical structure, and then further take those results and map it onto whatever source mesh that we wanted to use. And the other thing is, you know, the edges of the skirt have to twirl or lift first, so we take that into consideration as well. Okay, and our final topic for the talk is, cool, we have all these controls, but so far, the only control that we're giving to the animator is a single knob or slider to see how intense they want the effect to be. But going back, this is kind of the problem that we were noticing with other solutions, and especially as an animator, it's one of the things that bugs me the most. I want to have more control over the motion. So what we did is come up with a filtering mechanism to enhance, to give the artist control over the reactivity of each deformer. Do we want each effect to be slow and smooth, or snappy and fast and rapid? And turns out what we can do is just take a low-pass filter, apply it on our input signals, and if we have a small gamma value in the filter, it gives us smoother signals. If we have higher gamma value, it increases our high frequencies, and so we get snappier results. And here's a comparison between the two different filtration options. becomes extremely helpful when we try to combine different effects together. So we have 3 different deformers that we talked about, right? Well, when combining them, you can filter each of them differently to get different responsiveness. And this becomes very helpful. So if we use the same gamma value on all 3, these are 3 different deformers. We sum it together, and this is the untuned result that we get. Personally, I don't find this very appealing. If you were to go in, as you can see here, and individually tweak the gamma values for each effect, they combine to form something much more smooth and fluid and artistic. Looking at them side by side, you'll see how clean the arcs of the animation are. And the moment we've been waiting for. Here's a collection of our results. And in the interest of time, I think I'll move ahead. We are running late, right? So in conclusion, we created 3 different deformation effects. Each of these effects can be controlled independently by the artist as they choose, and moreover, their responsiveness can be tuned independently for further controlled combinations of effects. So our method is fast and easy to compute. It works out of the box on standard run-of-the-mill character rigs. Limitations? Well, it's not physically accurate. You can see from the diagram that we have no approach for handling self-intersections between meshes. In terms of performance, there's really low overhead for using acceleration or velocity. It's basically a negligible increase. So it's the same level of cost that you have with linear blend skinning. For acceleration skinning, all the results that you saw today were directly off of a CPU. We didn't perform any GPU implementation, but we did for velocity skinning, which is where you saw the monster and it was running fantastic. So if you're interested in digging deeper, our C++ implementation is available on GitHub from the URL that you see below. And with that, I'd like to once again thank my mentors, Victor and Damien, and open the floor to any questions.
All right, thank you, Niranjan, for your presentation. I think we have time for maybe one quick question. There's one right there, yeah.
Thank you for a great talk. I remember you mentioned that the artists used to manually tune everything to achieve fluent animation. So in your method, you mentioned that you use some different techniques to improve on that. So I wonder how many parameters the artists need to generate the examples you show us? And is this method generalized for every material and every kind of animation?
Oh, that's a very good question. Thank you. It had a lot of parts to it, so I'll try to break it into pieces. So in general, when artists are performing character animation, what they're doing is taking each skeleton on each joint on a character and defining at this point of time, where in space does this joint need to be? And you do that for essentially all of the joints on the human body. Now imagine doing that over a 90-minute film. It's insane. But when you go in and add more effects onto it to further add these kind of fluidity and rubber hose animation, which is what we were trying to get, it's not just a question of the animator's time, but also the character rig needs to be even more complex so that it can support movement like that. With our technique, what we essentially do is say that give the animators freedom to animate their character however they want, and we add our system essentially takes that animation, adds a layer on top of effects on top of it, which the animators can then tweak. And you asked about parameters. Essentially, what we were doing is for every effect that we have, the animator can control the intensity of the effect, and also because of the filters, they can control how snappy or how slow and delayed the velocity and acceleration settings are. So essentially about 3 knobs per effect.
Yeah, that's, thank you.
Thank you. Thank you for the question.
All right, unfortunately we are running quite late, but I encourage you to talk with Ranjan after the session today. And congratulations again, Ranjan, on the
Thank you. Thank you so much, Sheldon.
We're ready. Our second best, it's not second best, our next paper, which is the best HCI paper authored by a student, is Tutorials for Children by Children, Design and Evaluation of a Children's Tutorial Authoring Tool for Digital Art. And the student who is here with us is Ananta Chowdhury from the University of Manitoba, and her supervisor is Andrea Bunt, and I know she is online virtually congratulating you and jumping around and being happy. Okay, so please go ahead and show us what you got. Thanks.
Thank you so much, Dr. Phelps. It's really an honor, and I'm really thankful to my supervisor, Dr. Andrea Band, and to my family for their unconditional support, and also my lab mates for their continuous feedback on my progress. So let's start. So I am a PhD student, and it was my master's thesis. So I'll jump to it. So we know that with the increasing use of technology in our daily lives, children are spending more and more time with digital devices. And as HCI researchers, we want to make children's digital device use and their screen time beneficial for their childhood development. So in this case, engaging children in the creation of digital art can be an effective way, because art is known to have positive impact on children's childhood development. And in this era of digitization, digital art tools can open up new opportunities for children to be creative and express themselves. And with each digital art, children can explore new effects and neat features which might not be possible with physical art. So there are many potential benefits of digital art, but the process of creating digital art is not always straightforward, because generating visual outputs with complex tools can be difficult. And while there are many digital art tutorials available online, most of these are created by adults for other adults. And prior research says that children find these adult-oriented resources difficult to use for their advantage. So in this case, what if children could create drawing tutorials for other children? So if children incorporate the workflow histories of how they create a drawing or a drawing tutorial, it might help those children who struggle with creating digital art by themselves. Now you may wonder, like, why did we pursue this direction? Like, why even have children generate tutorials for other children? Well, literature from other domains have shown that children who create tutorials for their peers have many advantages. For example, children who create tutorials will learn effectively and will be able to think from others' perspectives, and it may provide them with a sense of accomplishment, increase their motivation to improve, and also can influence their sharing behavior. So it might be worthwhile to explore how children would feel about creating digital art tutorials for other children, given the positive benefits of drawing and creating tutorials. So now let's look at our contribution of this paper. In our paper, we provide insights into how we can support children in the creation of digital art tutorials with an authoring system. Then our paper provides insights into how children could use such an authoring system to communicate their workflow histories to other children. Further findings from our study and our paper illustrates children's attitudes regarding the idea of generating digital art tutorials for other children. So these are the main contributions of our paper. Now let's take a look at our methodology to address our research goals. As the first step of our research, to explore how children would feel about creating art tutorials for other children, we started with the low-fidelity prototype, because prior work have shown the effectiveness of low-fidelity prototyping in eliciting feedback from children. So we used this low-fidelity prototype in a participatory design session to better understand children's perspectives and their needs. So we involved the children in the design process. Then, based on the feedback from these participatory design sessions, we created a higher fidelity prototype, which we then used in a second user study to further explore this concept. So this was an overview of our methodology. Now, I'll discuss each of these in more detail, but let's first talk about what our approach to authoring and sharing workflows were while prototyping. So after iterative brainstorming and sketching, we decided that our general design direction to children's tutorial authoring would be to allow children capture their own steps while they are working on the drawing. So this was also based on prior literature that showed that most of the tutorials follow a step-based approach. So this was our basic template for the paper prototype. Here, each step will have a drawing step, the image of the drawing step, and some accompanying information. And our approach was to let children decide when they want to create a step. And we also wanted to allow children provide comments or tips associated with their steps. So, sorry about that. So this was our general design direction, and based on this, we developed a low-fidelity prototype, which we used in a participatory design study. So in the participatory design sessions, we elicited feedback from the children about our design approach. We had 8 participants in total, where we had 5 boy and 3 girl participants, and the age group was 6 to 11 years. So we targeted this age range because prior work has shown that children in this age range are typically able to think logically and make independent decisions. So now let's see how children actually interacted with our paper prototype in these participatory design sessions. In the participatory design sessions, at first we asked the children to create a drawing on computer using Microsoft Paint. And when they were creating their drawing and they were ready to save a step, create a step, they would let us know, and we will capture that step with a camera. These steps were printed out instantly using a Polaroid printer, which they used, like the captured steps, they used to create a tutorial with them using our paper prototype. So this is a result of our participatory design session with a child. And as you can see, she created multiple steps and added comments on pieces of paper and also added tool information with each of the steps. So we had sticky notes with all of the tools on them, which the children could drag over on the paper prototype. When the participants were creating the tutorial, we observed how they interacted with our prototype, and we also received feedback from them about what they liked and didn't like about their prototype. So that's all about our design sessions, and now I'll talk about some of the findings from our study. So from our study findings, we gained insights about the appropriateness of our target age range. In our participatory design sessions, we observed that the younger children who are 6 years old, they had difficulty in understanding the concept of capturing workflows. And the remaining 6 older children, they were able to grasp the concept better, which indicated that 7 to 11 would be a better age range for our approach. We had some insightful findings from the participatory design sessions where we observed that participants were enthusiastic about creating workflows for other children, and they also were interested to see others' drawings, others' tutorials, and they found this concept entertaining and thought it would help them to gain new ideas. Also, we received feedback from the children about our design approach, based on which we designed a higher fidelity prototype. So I will discuss some of this feedback from the study sessions in the context of this higher fidelity prototype. So let's take a look at some of the features of our prototype. The higher fidelity prototype allows the children to capture a step while drawing. So when the child chooses to capture a step by clicking the Save Step button, the prototype automatically requires the current step of the drawing and also the tools that were used in that step. The prototype also allows the child to comment about the step when they were capturing it. So this design decision was based on the feedback that we received from our participatory design sessions, where some children preferred to write comments while working on the drawing so that they don't forget it later. The prototype also shows reminders when the child seems to be forgetting forgetting to capture potential steps. And this was controlled by a wizarding interface. After the child indicates that they're done with the drawing, the prototype creates a step-based tutorial like this. And as you can see, each of the steps includes the tool information that was used in that step, and also any comments the child have provided while drawing. The prototype allows children to delete unnecessary tool information and also delete steps. Children can also edit their comments after they finish working on their drawing. The final version of their tutorial will be displayed by the prototype, and eventually it would be shared with their friends. So while creating this prototype, our goal was to use it as a means of further inquiry in another study. So we used this in a second study, which was supposed to be in person, but due to the COVID-19 restrictions, we had to do it online. So we had 16 participants, where the target age group was 7 to 11 years old, and we had 8 boy and 8 girl participants. So in this study, at first we asked the children to create a tutorial while drawing something using our prototype. Then there were some survey questions which we used to elicit feedback regarding the design decisions about our prototype. And we also conducted semi-structured interviews with the children to gather some qualitative data on how children feel about using such a tool. Now let's take a look at some of the tutorials created by our participants. So this tutorial is created by an 11-year-old boy participant, and as you can see, he created multiple steps in the tutorial and tried to provide quite detailed and informative comments. And on average, our participants created 7 steps per tutorial, and almost all of them provided comments with their steps. And in general, most of our participants liked having the step creation interleaved with their drawings. So let's look at another example. So this was created by a 7-year-old girl participant. And she was having difficulties using the keyboard and spell the words, but still she put a lot of effort into crafting the comments. As you can see, each step had one comment attached to it. So like this participant, majority of our participants were positive about creating steps and crafting comments. And majority also wanted to create a tutorial again using such kind of tutorial authoring system. And an interesting observation from our study sessions was that children's step creations were based on the elements they added to their tutorials. So the step creation was mostly conceptual, and in particular, it wasn't based on the tools that were used in the steps. So these were some of the observations from our child-generated tutorials. Now I will discuss some of the interesting findings from the interviews. We received important feedback from our participants on the features of our prototype. So participants generally liked having the control to save their or capture their own steps, but some children actually found it a bit distracting. They didn't like that it diverted their attention from their drawing. Then we received mixed reactions towards writing comments. So most of the participants believed that commenting is helpful because it provides information about their drawing. But at the same time, some participants struggled to verbalize their thoughts into comments. So they felt that it was sometimes hard to explain the steps the way they wanted to. Most participants liked the tool information provided with each step because they thought it gave a clear idea of what tools are needed to attain a certain effect. But some participants wanted to have some more information other than the tool name and icon. For example, other properties of the tool, like brush size or the color of the paint. From the data, we also learned about some of the incentives that motivate children to create and share tutorials. The main incentive for most of our participants was to help others to learn and improve their drawing. So some of the children enjoyed the fact that they are creating a tutorial in order to instruct others. Another incentive was to showcase drawing skills. Among the children who were particularly confident about their drawing skills, they wanted to share their tutorial with others so that other people can appreciate their art and try it out. Both of these findings resonated with our expectations, but we also had some other incentives that we didn't really anticipate. For example, for some participants, one of the incentives to share workflows was to assess their own skills. They wanted to see how understandable and helpful their tutorials were to others. Some of the children also wanted to compare their drawings with others to see whether others were able to create a better version of their drawings by following their tutorials. A few participants mentioned that they wanted to create a tutorial to keep a record for themselves. By generating a tutorial of their own drawing, they can review it whenever they wanted to recreate it. And it indicates that even if a child is not comfortable to share their drawing with others, they can still create tutorials for their own record. While our research focused on children's creation of tutorials, we also asked children how they would feel about following others' tutorials. The main reason for our participants to follow others' tutorials was to learn from others and gain new ideas and inspirations. Another reason was to improve their drawings from others' tutorials. And an interesting observation was, like one participant mentioned it, they wanted to use tutorials to make the author feel happy about it. So the satisfaction of making someone happy by using their tutorials was an incentive for this participant to follow others' tutorials. So to summarize the key takeaways from the study, we can say that the majority of our participants were interested and capable to create tutorials. They seemed to put effort in generating the steps and crafting the comments. And our participants liked having the tutorial generation interleaved with their drawing. And they also liked having the control to save their own steps. And finally, our participants had a range of incentives to generate digital art tutorials, which ranged from helping others to create a record for themselves. Now I will talk about some of the interesting discussion points based on our findings. So as we discussed before, children liked controlling their step and they liked having the tutorial generation interleaved with their drawings, but some participants didn't like that it diverted their attention from their drawing. So in this case, is it possible to have an automated step capture feature? So it might help those children who want to create tutorials, but they find it distracting. They feel that it diverts their attention from the drawing. So it can be a solution, but the problem is we don't yet know how we can do that based on the findings that we saw. So we saw from the tutorials that children's step generation was based on their elements, the elements they added to their drawing. So how can we automate this step creation that is conceptual? So that can be challenging. On another note, we got some preliminary insights into why children would like to follow another children's tutorials. But we don't really know what the pros and cons of following another child's tutorial would be over an adult's tutorial. So to get some initial idea, we looked at some adult author tutorials available online, and we found some primary differences with our child-generated tutorials. So we found that adult tutorials were detailed and followed a structured approach, whereas children's tutorials were simpler, but they were really creative in adding elements to their drawings. So now the question is how children would use these two types of tutorials. So it might be possible that adults' tutorials could be better for learning new drawing techniques, whereas children's tutorials could be better for younger children to follow and also might inspire creativity. Finally, I wanted to discuss some of the pros and cons of the remote study. So we saw that in our studies, children sometimes were distracted by their siblings, and there were internet issues, and sometimes parents were having difficulties setting up the study, which made the kids impatient. So these were some drawbacks, but at the same time, we had some advantages that we didn't anticipate. So the remote study led us to recruit internationally, and also the parents did not have to find time to bring the kids to the lab, which led to more flexible scheduling. Findings from our studies also highlight interesting future research direction in this space. So in the paper, we mostly focused on how children create digital art tutorials, but we didn't investigate how they might share these tutorials in an online platform, which requires further study. And in our paper, we have already discussed children's interest in following another child's tutorials, but we didn't really explore how children would actually consume these tutorials. So in a future study, we can explore what we might expect if children were to use other children's tutorials. Further, in future, we can explore the impact of using our tutorial authoring system in a longitudinal study. For example, how children might improve their drawing skills through a combination of viewing others' tutorials, teaching others, and reflecting on their own process. Finally, another interesting research direction is to explore how we can apply our design approach to other kind of creative activities that involves complex software. For example, how can we support children in the creation of programming tutorials or 3D modeling? So that is all from me. Thank you so much for listening, and now I'll be happy to answer any questions that you may have.
I think we can sneak one quick question in. I think there is one coming on the virtual. All right.
Thanks, Ananta, for the wonderful presentation, and congratulations again.
Thank you so much.
I have many questions, but I'm going to stick to one. I was just wondering if you observed any emergent behavior in children in terms of, because drawing is a very embodied activity. So if you are looking at a tutorial, and children tend to add their own things to what they are looking at. So did you see children looking at a tutorial and adding their own perspective to it and coming up with something different?
Thank you for the question. So actually, in our studies, we actually wanted children to create tutorials. So we didn't actually get focused on how they would use another child's tutorial. But what we did is we showed a sample tutorial and we asked them whether, how would they feel about following this kind of tutorials. But what you have asked, this is really interesting, and I think this requires further exploration.
Thank you.
All right, thank you. And Maria, I'm very sorry. I know you wrote a nice question, but I think we're going to have to move on, and perhaps Ananta can answer that a little bit later in Discord. All right, so let's thank you very much for your nice presentation. Here's your reward. You're welcome. All right, so that, this concludes the scientific portion of GI 2022, and how nice to conclude with children's drawings and thoughts. And Naranjan, I hope you maybe identified a future animator. So we've just got a few minutes for the closing parts. We've got a couple of awards to complete, And then I think we're going to hear from Victoria. Sheldon, shall we maybe do the poster, the best posters? We'll start with the closing. Okay.
Oh, I'm missing my adapter.
Yeah. No problem. Thanks for your patience. He has the slideshow. I don't have the slideshow. So we have to wait. Oh no, you gotta come up. You're coming up to give them. You come up.
I think this is working. Yep. No. Can you?
Oh.
Did you share? Okay. Oh. Here, Adrian?
Adrian?
Yeah, sure. Do you want this?
Yeah. Thank you.
Okay. So, GI 2022 is coming to an end. Thanks for being here, everybody, and everybody that's remote right now. It's been a wonderful few days, well, since earlier this week, Monday, when we had our workshops and all the great paper presentations and award talks, and it's just been, well, very fascinating for me and a very exciting week, as I'm sure it has been for you. And you probably haven't seen much of this gentleman right here this week, because he's, in addition to being our all-star general chair, he's also been our tech support this week. He's responsible for the technical setup that we've had here at the school to do the hybrid conference, so in person and streaming.
Yeah.
I don't know, do you want to say anything, Adrian?
Yeah, I want also to thank Leslie that developed the automatic system. Basically, it's how we operate it. It's like we program OBS such that we can easily change the shot and so on. So it's why you see like we have all the shots and so on. Every time it was Leslie that developed the system. She cannot be here today, but we thank you, Leslie, for developing this system.
Yes, thank you, Leslie, who was our hybrid chair. And thanks to the whole organizing committee. It's been fantastic working with them over. Well, personally, I found it fantastic to work with all of you over the past year or so planning this conference. But Adrian, your hard work, like we really want to recognize like, the amount of energy you put into this over.
We have a surprise award.
We have a surprise
okay.
present or gift for you,
yeah.
Deborah.
Right. Okay. So, sorry, it's a bit squished. So I just want to let you know that we wrapped it in a limited edition bag.
Okay.
With a very nice pin from a really nice university that's very fancy.
Very haute couture, yeah. Good.
Okay,
so thank you very much for doing everything that you've done. And I mean, you worked really hard.
Thanks, Adrian.
Thank you.
Thanks, Adrian.
So thank you everyone to join us, and you know there is also something that was not possible to do is like with all the student volunteers that also helped me. So I just want that they join on the stage to that on the YouTube like people can see you.
Yeah, come down, as many of you that are in the room as possible. Please come down.
Andre, can you change to award? Oh, yeah, you already changed it. Okay, and unzoom on the camera. And I want to say that, I'm very supportive that the students wanted to volunteer for the conference, because for many of them, it was the first time that they have in-person conference due to the COVID. And so thank you again for your help for running the system and doing all the like annoying tasks, right? Okay, thank you again. Okay.
Okay, we need one of you to switch back the the camera feed, please.
Yeah. Okay. We just wait, like, if someone can reselect slide for base. Yushu, can you just do presenter live?
So we also want to thank especially our sponsors that help make this whole conference possible. Once again, we'd like to thank Roblox, CM Labs, Intel, Huawei, Adobe, Reality Labs, and Research, and of course ETS, where many of you have been over this past week, and our parent organization, CHCCS. And stay tuned for the CHCCS AGM that's happening just after this, the closing ceremonies. But thank you sincerely once again to all the sponsors that help make this possible. And yeah, absolutely. Now, yeah, we partner with some computer graphics and visualization journals on selecting some of the strongest papers that you saw over this week, and we invite them to send extended versions of their papers to two journals that we have partnerships with, one being IEEE Transactions on Visualization and Computer Graphics, TVCG. And so we're inviting the following papers to send extended versions of their work to these to IEEE TVCG. So congrats to these two papers that are being invited to send extended versions of their work. More details will follow. And the other journal that we partner with is CNG, Computers and Graphics, and we're inviting these papers to send their work to Computers and Graphics extended versions. So congratulations to those authors as well. And next up we have the poster awards, the best poster awards. And I'm going to let Fatima take over from here.
Thank you. Okay, we have two poster awards. I would like to invite Samuel Lefebvre for poster Gestures in VR with in-situ feedback. Please. Congratulations.
Thank you.
And the next best poster award goes to Kavosh Jazar for fast approximate animate impulsive.
And thanks to the judges, Simone and Chatal, right here. I don't think Simone is here, but you probably saw him walking around and looking at all your posters. They worked very hard to evaluate the posters. So, GI 2022 comes to a close, and we're looking forward to see you all next year in UVic, in BC. So next year's chairs are going, whoa. Okay, we're switching over. We have a live feed from them. Excellent. I'm going to let them take over because our job is done, and you'll see these nice folks next year.
Can everyone hear me? Oh, I'll assume that everyone can hear me. So
Yeah, we can hear you.
Oh, hi everyone. My name is Miguel Nacenta, and I am the General Chair for GI 2023. And we are very excited to host Graphics Interface in Victoria, British Columbia. We want to acknowledge first, with respect, the Lekwungen peoples on whose traditional territory the University of Victoria stands and where the conference will take place, and the Songhees, Esquimalt, and Wusanich peoples whose historical relationships with the land continue to this day. So I want to also introduce part of the team. So Kang Ying and Charles Perrin will be the technical program chairs. And I actually recruited Charles to be translating in the second official language of Canada. So we are planning a vibrant program, exciting speakers, great social events, and opportunities for learning for everyone.
On travaille déjà pour avoir un superbe programme.
The conference will take place at the beautiful UVic campus, which is 15 minutes by bus from downtown.
La conférence aura lieu à l'Université de Victoria, qui est à 15 minutes du centre-ville en bus quand il fonctionne.
And a 10-minute walk to Cadborough Bay Beach.
Et à 10 minutes de la plage de la baie de Cadborough.
We are negotiating competitive rates for accommodations on campus.
On travaille pour obtenir des logements à des prix non outranciers sur le campus.
But of course, you can decide to stay in beautiful downtown Victoria, which has amazing restaurants, pubs, coffee shops, music and art venues, and much more.
Mais bien sûr, il y a aussi de nombreuses options au centre-ville. Vous trouverez un grand nombre de restaurants, pubs, cafés, activités touristiques et culturelles.
We hope that you will take the opportunity to explore also the nature around here with amazing hikes, parks within the city itself, and many, many activities.
Donc Victoria et ses alentours, c'est un endroit magnifique pour les amoureux de la nature, bien connu pour ses nombreuses randonnées et aussi sentiers cyclables.
You can take in the ocean, hills.
Vous pourrez contempler l'océan, des collines,
old growth forest,
des réserves biologiques avec de vieux arbres pleins de mousse,
and even alpine landscapes.
Et même une imitation des Alpes.
Getting to Victoria is easy from most places in Canada with direct flights from many provinces or indirectly through the Vancouver airport, which is a short flight or a scenic ferry ride from Victoria.
Et Victoria est accessible par avion, ferry ou même vélo si vous êtes vraiment motivé.
We are still looking for people to help us make GI 2023 very exciting and useful for you. If you have ideas, comments, or want to be involved, it does not matter where you are or your seniority in the community, we will find ways to put you to work.
On encourage tout le monde à nous aider à faire de GI 2023 un succès. On recherche des personnes motivées pour nous aider à organiser la conférence.
We have prepared a short survey at the address that you can see on the screen. And you're also welcome to write to me directly with any suggestions or if you want to volunteer for any position that has not been filled yet.
Donc vous pouvez vous porter volontaire ou nous faire savoir vos idées en remplissant le formulaire à cette adresse. Vous pouvez directement envoyer aussi un email à Miguel si vous voulez contribuer à remplir sa boîte email ou courriel.
So see you in Victoria.
À bientôt.
I think that's it. Thank you, Miguel and Charles. And we'll see you next year. And thanks everybody for coming. We're going to take a very short break, say 5 minutes, and then we're going to start with the CHCCS general meeting. If you're interested to participate, please stick around.